You do have a clock. Okay. So I'll give everybody a warning at like 2 minutes. Okay. So we're going to get going. So of course these are the 5 presentations for Astronomy 98. I think everybody in the room is familiar with the format, but for the web, we have, I'm going to stand to the microphone, the students at Harvard engaged in a 1-semester research project, and during that time they're also having weekly dinner meetings with members of the community at the Center for Astrophysics. And this is a chance to hear about the research that the students have been up to for the semester. So the format is the students are going to give a 10-minute talk, and then there's 3 or 4 minutes for questions, and we will do our best to keep on schedule. So our first speaker is Jeremy Dietrich, and he's going to talk about the feasibility of water detection in the atmospheres of Earth twins. Okay.
Thank you very much for that introduction. As you can tell, H2O detection feasibility in exoplanet atmospheres, specifically Earth twins. First little introduction. We know of 2,000 exoplanets in over 1,200 systems. Most are discovered via 2 methods, the radial velocities and measurements and transits. And the big question is, do we want to know, are there planets with life? So we can search for extraterrestrial biosignatures in the planetary atmospheres. Stuff like molecular oxygen, carbon dioxide, ozone, methane, and a very important one, which we know on Earth, is water. To do this, perform high-resolution ground-based spectroscopy using planned spectrographs similar to GCLEF for the GMT, and HEROS and SIMPLE, and stuff on the European Extremely Large Telescope, EELT. And we're looking at wavelengths less than 1,000 nanometers because the Earth's atmosphere is very stable there. We take detailed spectra of the planet transits, the starlight will be passing through the exoplanetary atmosphere, so it'll dominate the transmission spectrum. And we also see Earth's spectrum from the ground. And since I'll be looking at Earth twin planets, I'll be seeing the exact same spectral lines. So we'll need to account for the only way we can see them is through radial velocity shifts from the system. So here's an example of the simulation spectra I use. The top is a telluric spectrum from the Earth. And there's also a very small spectrum of the exoplanet itself, but it's a factor of 10 to the 5 smaller than the Earth. And then the sample spectrum for an M4V red dwarf star, which is the star I'll be using for my simulation system. So I created the simulated exoplanet spectrum system of an Earth twin planet around an M4V red dwarf at 10 parsecs. Previous studies show that M4V red dwarf stars are the best to limit the number of transits required to observe other biosignatures such as oxygen. So I created the simulated spectrum of the transit and a baseline outside the transit, and then subtracted the baseline flux from the transit. So we get the signal of just the exoplanetary flux, but the noise of the signal is added in quadrature instead of being subtracted out. So I determined the flux of this system for 4 different telescopes. 3 current or planned telescopes and 1 hypothetical. So Keck, currently in use, the Giant Magellan Telescope, GMT, and the European Extremely Large Telescope, EELT, which are planned telescopes, and then the hypothetical humongous telescope, which I call the HHT. These have diameters of 10 meters, 25 meters, 40 meters, and the hypothetical will be 100 meters, just to test. And I used the Vega 0-point values in the distance modulus equation to calculate the fluxes. And from there, I calculated the random noise values in parts per minute. I disregarded correlated noise from the instrument. That would be a little bit more in-depth. And the one transit noise was between 30 to 100 parts per million. So it was actually very good with these spectrographs. So in order to see the lines, I mentioned we needed to have a radial velocity shift in the system. So the radial velocity will cause a shift in the spectrum, the Doppler shift, where the lower frequency means that the system is moving away from the observer, where d nu over nu is delta v over c. And then I can cross-correlate the observed spectrum with a model of the telluric spectra. And what will happen is I'll receive 2 cross-correlation peaks. They will correspond to the two different signals that we'll be seeing through the atmosphere. One will be the main peak will be the telluric, cross-correlating with itself. And the offset, smaller one, will be the shifted exoplanetary spectrum, correlating with the telluric, because it is a model of the same spectrum. And the ratio between the two peaks will determine the percentage of the lines of the exoplanet that we'll be able to detect. So here's a picture of one. This is of 100 kilometers per second blue shift. So it's slightly closer. And then the ratio of the peaks is, again, the detection line, detection percentage. So I performed a grid of radial velocity values from negative 150 to 150 kilometers per second by 3 kilometers per second. And I performed a cross-correlation at each value. And if I had a ratio of peaks greater than 50%, I defined that as a detection window. So that is a radial velocity for a system in which you can detect the lines. And I calculated the percentage of these windows across the grid. And I tested, for each of these values in the grid, I tested multiple noise values as well. And I plotted the radial velocity shift versus the cross-correlation peak ratio. Lines are not detected at the radial velocity of 0 because they will match exactly up with the Earth. And at large radial velocities, there are so many lines, water lines in that area, that it's hard to correlate them when they're so far apart from each other from the original method. So this is a cross-correlation ratio of at a noise of 5 parts per million. So it's slightly asymmetric, mostly because of the noise, but also because the spectrum itself is not rotationally symmetric. So the results were highly dependent on the noise. The percentage of windows varied greatly, even at 25 parts per million. And I started getting nonsensical values, noise even at 50 parts per million or even less. One of the reasons why is that it might be capturing noise as signal because the signal is so small that any noise could end up randomly modeling the same exact thing we're looking for with the signal. So I need to get very low noise values, which I achieved through taking multiple transits, because the noise goes as 1 over the square root of the signal. This is a graph of the noise and the percentage of the windows. So with no noise, I had about 22% of the areas in the grid were windows, and then it kind of went up after that, which didn't really make sense unless you take into account that I could be getting noise as signal, and the standard deviation, 1 sigma, varied dramatically at the end. So with an M4V habitable zone period of 16 days, and the noise dependent on the number of transits, we need 2 to 15 transits based on telescope aperture for acceptable noise. In a perfect world, this would take 2 to 8 months. So if you get the entire transit every time for every 16 days. However, previous studies have concluded that you're likely only to get about 10% of all the transit time. So that would take about 1 to 5 years. This is consistent with previous studies of oxygen. Rather than Lopez Morales 2014 had 5 to 10 years, a similar order of magnitude. However, they had a much more stringent simulation where they included refraction effects, they included red noise, correlated noise effects, and they also included their lines were oxygen lines, which were different in structure than the H2O lines I'm looking at. So, final discussion. H2O detection is feasible at current parameters of spectral resolution around 100,000, but the noise needs to be less than 25 parts per million for it to be viewable. I would recommend a more accurate simulation, taking into account correlated noise and atmospheric refraction effects. That would be a much more detailed simulation and probably produce a better result. I also recommend using higher resolution because if you can get extremely detailed spectra, although that would split the signal amongst more bins, and to see whether or not there really is water elsewhere in our universe. Thank you.
Great. Okay.
Questions?
Questions?
Yes.
So in this simulation, did you assume that the atmosphere of the exoplanet has the same composition as the Earth's atmosphere, or did you vary the amount of water in the atmosphere as part of your parameters?
So for this simulation, I assumed a similar overall composition as the Earth. However, I didn't vary. I kept it consistent or constant through the height of the atmosphere. So again, something that could be done is what I did was I assumed that the ratio, the percentage of water was constant all the way. But we've known that, at least in the Earth, that water is concentrated at the lowest 10 kilometers or so of the atmosphere. And that could be, if we're looking for exactly like an Earth, we could take that into account as well. Whereas I just said it was constant all the way up to 100 kilometers or so above the surface of the planet. Yes?
So that one plot you showed where the windows actually went up with the amount of noise you had, I think you're probably right that that can't be the right answer.
Right.
So I was wondering, did you look at the signal to noise? Because I guess I would expect, so this is basically saying as the noise goes up, your noise actually takes the signal in some sense.
Right.
Like, could one remake this plot for signal to noise, and also does signal to noise depend on the distance of the system from the Earth?
Yes, the signal to noise does depend on the system from the Earth. I could probably recreate this with signal to noise, but I imagine the signal. I'm not exactly sure how that would actually affect that, though. I did not look at that, and I apologize for that. But yeah, I know that the signal faking is not something that I was expecting to come out. I was expecting it to drop, if anything. But that's what ended up happening.
But just so I understand, so there you didn't change the signal, right?
No, the signal
So
along this whole thing. I'm
adding more
just
noise.
cranking up the noise. The signal's not changing.
Yeah, so I apologize. I said something unclear. I guess what my idea was is that you probably want to have a window, but also a signal to noise greater than 1. So if you impose that cut to that, would give you.
Oh yes, that's true. If I set a limit for the signal to noise, yes, that would probably change that. Thank you.
So where'd you get the telluric spectrum? Did you generate that from a model? Or
My acknowledgements. It was generated by a model from Dr. Gonzalo Gonzalez Abad. He's generated a very high resolution model of the Earth telluric spectra, and I'm very glad that he allowed me to use it for this project.
So is water easier to detect than oxygen? Or is oxygen easier to detect? Or are they both impossible?
I'd say they're both extremely hard at this time.
But it is water. See, the water has so many more lines, perhaps. Perhaps it's easier.
Water has so many more lines, which in my opinion, I would think it'd make it a little bit easier to detect because there's so many of them. You might catch some of them in the shift. However, they are weaker than the oxygen line, so that would also make it a little bit harder to detect. And we're at that point in the spectrum where we're looking between 800 and 1,000 nanometers. The current CCDs drop off dramatically around there. So the throughput gets very low, and it's hard to detect a lot of signal there. You could also look at water in the infrared, where the lines are deeper. However, the atmosphere is a lot less stable there, and it'll be a lot different of an observation trying to look through the Earth at infrared levels.
And what bandpass did you restrict to here?
I was thinking between 780 nanometers and 1,000 nanometers. Yes.
Okay, any final questions here? Okay, well great. Well, let's thank them again. Thank you very much. Give us a microphone. And hand over to Andy. I'll bring up the presentation here. All right, Andy. Just play.
Yeah, that should be fine.
Okay. All right. So our next speaker is Andy Mayo. And,
Mayo.
Okay, sorry, Mayo. Pardon me. And he's going to tell us about a catalog of data of secondary eclipses of exoplanets. Okay.
Thank
So I'll
you.
give you a warning at 2 minutes.
Sounds good. Thank you. All right. So, I'll be talking about a catalog that I created for my research of secondary eclipses. So let's jump right in. Little overview. First, I'll go over a little background on secondary eclipses. Then I'll lay out a bit of description for my project. Then I'll talk about my results. And I split them up into 3 groups. The significant and yet self-evident, pretty obvious results that I found. and then the correlations that I found in my catalog, which were caused by biases. And then after that, I'll look at the interesting ones that I found. And then I'll have a little conclusion. So first of all, what exactly is a secondary eclipse? Basically, a secondary eclipse is when you've got your star. And a transit, as most of you know, is when the planet passes in front of the star. Secondary eclipse is simply when it passes behind. So the thing with the secondary eclipse is that it's much more difficult to detect. Where a transit can cause a 1, maybe 2% dip in light, a secondary eclipse typically has a dip on the order of hundreds of parts per million. So it's much more difficult. On the other hand, you can learn a lot more about the atmosphere of the exoplanet from a secondary eclipse. And that's simply because the light that is obscured has reflected off of the planet. So you can look at in various bands how the dip varies, and from that you can learn whether the planet has water or methane or carbon monoxide or other common molecules. So for my project, I created a catalog of every exoplanet that has secondary eclipse data. Now I can't guarantee completeness, but it's fairly complete. I had 69 exoplanets in 67 systems. And I compiled all of those together and included stellar and planetary parameters in addition to the secondary eclipse data. And then I correlated every parameter in the catalog with every other possible parameter and looked for potentially interesting relationships. Due to time constraints of the project, we only had 8 weeks. I couldn't do a rigorous statistical analysis, but I was able to find some interesting results nonetheless. So it was a lot to do, but. So some of the significant results, which were very obvious, include, for example, the magnitude, the brightness of the planet, of a given planet in one wavelength versus the brightness in another wavelength. That's highly correlated simply because the size of the planet, the albedo of the planet, are the dominant effects in determining the brightness of the planet, and as well as the temperature. So you don't see a lot of variation from one wavelength to the next to first order. There is some scatter, and that's where the interesting stuff is, but you see a very strong correlation. Another very obvious one is the correlation between the brightness of the star in one wavelength versus the brightness in another wavelength. Again, that's going to be very strongly correlated, and although it's very significant, it's not very interesting. A lot of other correlations that I saw were simply caused by biases. So the example I have here is the distance of the system compared to the brightness of the planet. So as you can see, these planets are at a very great distance from us, and they're also very bright. And that's simply because you're not going to see anything up here. That's very far and very faint. And you just don't have the detection up there. You're going to have all of this stuff. You can't see it. And so that's a bias that's going to induce a trend in your data. So there were lots of those kinds of trends as well. But the interesting things that I found. Primarily, what I saw was an interesting relationship between metallicity and certain color indices. Color index is the difference in magnitude from one wavelength band to another. So in this example, we have a correlation between the metallicity of the star compared to the 4.5 minus 5.8 color index. And it's a very interesting trend, and it doesn't seem to be caused by the temperature of the planet. You would expect that there might be an effect of the temperature, but it doesn't seem to be very significant if you account for the temperature as well. Additionally, I found another interesting correlation between metallicity and another color index, the KS band minus 4.5 micron band. And this is negatively correlated, whereas the other was positively correlated. You may notice that the commonality between these two correlations is the 4.5 micron band. So my hypothesis is that The 4.5 micron band is this green line right there. The 6.3 micron water line, it's a very deep absorption band caused by water. And I believe that the 4.5 micron band is affected by the water in a given planet. And if you increase the metallicity in the planet, that's going to mean there's more water in the planet's atmosphere as well. And that would explain why the KS band minus the 4.5 band has a negative correlation. However, you also have a positive correlation between KS and, between 4.5 microns and 5.8 microns. Now, you would expect that if the 5.8 micron band is deeper inside this absorption line caused by water, you would also have the same type of correlation. And yet you see an inverse correlation you wouldn't expect. That is to say, this is a positive correlation, whereas you would expect a negative correlation if 5.8 is more significantly affected by water. Now, I don't have an ideal explanation for that. My best guess at the moment is that 4.5 microns is also affected by carbon monoxide, whereas the 5.8 micron band is not. So if you increase metallicity, the 4.5 micron band may be affected not just by water, but also by carbon monoxide, and that could cause it to be more dependent on metallicity than the 5.8 micron band. If that's the case, then we're seeing the effects of both water and carbon monoxide in the two trends that I saw. So that means that metallicity, as you increase metallicity, the 4.5 micron band is most significantly affected by these variations, which would cause a positive correlation there and a negative correlation here. This correlation wouldn't be as significant because the 5.8 micron band is also affected by water, just like 4.5 microns. So that's my current hypothesis. There will certainly need to be more testing of that and more data collection as well. So that's why we should expand the current set of secondary eclipse data as well as improve the data that we already have through improved instruments for precision photometry. That way we can detect more secondary eclipses, and the secondary eclipses we've already detected, we can improve the measurements, improve the error bars. And that'll allow us to find new and interesting relationships, as well as see if the relationships we've already found are as robust as we expect. So that's my presentation. I can take any questions.
All right, questions for Andy?
Yes, yeah, Andrew.
So, out of the 1,600 pairs you correlated, how many spurious correlations do you expect to find?
So I would say roughly like a quarter or a fifth of them were what I would call significant. And that's simply because I correlated everything with everything. So that includes every band for the star versus every other band for the star. That's 30 or 40 pairs that will be highly correlated. Same goes for the planet. I also included a parent magnitude as well. So you have a lot of correlations there. So going through, you can separate them into a few categories. Those were the most significant categories, the ones that I covered, but there are other subtler correlations that I found which were also not too interesting. So that would be the main breakdown.
Is that really what is that what you were asking?
Yeah, is that?
Well, I was trying to get at if you blindly correlate a lot of things, then some fraction of the time you're going to have two signal results. That's going to be about 5% of the time.
Mm-hmm. Mm-hmm.
So are those two plots that you showed significant when you consider how many things you look through to get them?
Mm-hmm. It's an excellent question. Unfortunately, I wasn't able to analyze very rigorously the statistical processes that I went through. For the most part, however, if you look at, for example, instead of 4.5, if you look at like 3.6 microns compared to the KS band and the 5.8 band, a number of other less statistically significant but still interesting relations back up the relationships that I saw, which suggests that there is something going on. Whether or not I have the appropriate explanation is up for debate, but I do believe that we are seeing something in these relationships. More data needs to be taken, and certainly some more analysis of the catalog that I have, but I believe that the relationships that I found are there. I think I saw another question. Yes?
Yeah, well, I kind of like in the similar theme, but does it make sense at all, I guess it's a question for anyone in the audience too, does it make sense at all to simply like take a p-value for these correlations given just like the x and y coordinate, not considering the error bars, or is there a more would it be like a more rigorous part of the project to assign like a very numerical statistical significance to these plots?
Yes, so I believe you're asking what would be a better way of statistically analyzing the data? Yes, so what I would have preferred to do as opposed to what I did was Pearson correlation test for the most part. But that wasn't like the final say in the matter. If I saw interesting relationships, I tried to interpret them appropriately. And sometimes the Pearson correlation test did not do as well as expected, even when I saw something that looked like a relationship. If I had more time, and what I would like to do in the future is run some MCMC processes on the more interesting relationships, as well as look at how many relationships I would expect to see given the number of correlations that I investigated, sort of what Andrew was talking about. Sort of doing those would give me a much better statistical foundation on my analysis. Yeah?
If your 4.5 micron ratio to the 5.8 micron ratio is sensitive to the water line, could you potentially use that to say, like, these are the most interesting candidates to follow up with?
Yeah, potentially. The issue is that the slope wasn't very steep for that relationship, and so it would be difficult for a given planet to see if it falls on the line where you expect it to. Additionally, if I'm right about the presence of the carbon monoxide affecting 4.5 microns as well, then that's another factor to consider. So potentially it could be useful, but that would require some further investigation.
So why did you first invoke water? Couldn't you just explain everything with saying, I thought it was really neat to see this potential metallicity correlation.
Mm-hmm.
I haven't seen that before. When they designed, when Spitzer designed those filters, I think they picked the band, that second band, so that it would capture that CO. I think part of the motivation
Yes,
for
yes.
the bands was that CO feature.
Mm-hmm.
So why do you need to invoke water? Why can't CO explain both the correlations you see?
Because if you only invoke the CO, it also, to vary the CO as much as you would need, I believe, would also affect other bands more than it appears to be affecting them.
I see. Other colors.
Yes. And so I don't believe by itself it would be significant enough. I would need to look into that more, but I believe that's the broad explanation, that varying the carbon monoxide as much as would be necessary to create the correlations I found would create other effects that you would see elsewhere, which I was not seeing. So, yeah.
Another thought is if some of the stars are cool enough, they will have CO.
Mm-hmm.
So then you get an interesting effect where,
Mm.
as you vary the planet's brightness, you do see a CO effect, but it just has to do with the star's CO.
Yes. No, that'd be very interesting to look into as well. Yeah. Are there any other questions? I believe I saw. Yes.
I guess from my own background, how are these metallicity measurements made? What line ratios are used?
Yes. So metallicity, I took all of these from literature and from past catalogs that I compiled together. So there's potentially a number of different ways in which these measurements were made, but I believe they're all the correct iron to hydrogen ratio measurements, but I'm not sure in particular how each one was compiled.
Wavelength, it's not necessarily infrared, these measurements, it could have been from optical as well?
Potentially.
Yes.
Yeah, they are almost
Yes.
certainly optical.
Okay.
Okay, any other questions for Andy?
Okay. Oh,
Well, thank you very much.
did you? Sorry.
It was fairly flat.
Oh.
Let's do it.
Thank you.
Okay. swipe over the microphone there, and I'll bring this up here. I'm going to plug this in. Yeah. This guy?
Yes.
Here's this if you'd like it.
Yep, thanks.
Okay, great. All right, so our third speaker is Juliana Garcia-Mejia, and she'll be telling us about some design considerations for the installation of an iodine cell on the trace spectrograph. Anybody here built the trace spectrograph? There you go. All right. You should put your hands up. I was asking you a question.
All right.
All right.
Hello, everyone. My name is Juliana, and today I'm going to be talking about design considerations in the installation of an iodine cell onto trace. And just to remind you, trace is the Tillinghast reflector Eshell spectrograph, and it is mounted on the Tillinghast telescope that you see in the background. First and foremost, the goals and motivation behind my project. We want to install an iodine cell onto the 1.5 meter Tillinghast telescope in order to reduce Doppler shift by an order of magnitude from the current 20 meter per second precision. And although the science motivations are many, one of the relevant science motivations is looking for planets orbiting bright stars with solar type spectra. And we'll go into the details of how the iodine cell will allow us to do so. But before, I think it's very relevant to understand what exactly is it that causes radial velocity measurement errors. So this is a schematic representation of the optics of how trace currently works. Essentially, we have a stellar beam that is focused and collected by the telescope mirror. And without the fiber that you guys see depicted over there, we would have the beam unevenly filling the spectrograph slit. So the way trace works is it uses a fiber optic cable in order to scramble the light and smear it, and therefore reduce that instability in illumination. But although we have solved that spatial error in radial velocity measurements, we still have some errors that occur due to other spatial and temporal errors, other temporal and spatial issues. Namely, one of the most important ones is that we're using a comparison lamp to take reference spectra before and after we have obtained the stellar spectrum. And that means that the light that is coming into the telescope mirror is going to traverse a slightly different path through the spectrograph from that is coming from the stellar beam. So this is exactly what we're trying to avoid by installing the iodine cell. And the iodine cell is going to go in between the converging beam and the fiber. And what it's going to do is that it's going to allow us to take both reference and stellar spectra at the same time. Sorry. In order to show you schematically what exactly is it that is happening inside the iodine cell, I am going to use Butler's 1996 model, where spectra are taken through an iodine cell are modeled as eye observations. Essentially, what's happening is that as the stellar beam crosses the iodine cell, we have gaseous iodine kept at 50 degrees Celsius inside the cell, and this iodine acts as a transmission filter against which we can impose thousands of extremely sharp lines on the starlight. And the reason why we use iodine is precisely because it has many sharp features in the 5,000 to 6,200 angstrom range, and it is also non-lethal, which is always good, and it produces many, and it is a very stable molecule. Okay, so in terms of our preparations for installing the iodine cell, I'm going to run you through a schematic of how this whole optical setup kind of looks like in the actual telescope. So we have an iodine cell, and notice that the iodine cell has two different chambers. The chamber on the right, where you'll see a little bit of yellow That's the chamber where the iodine is, and the chamber on the left is an empty chamber, and that'll be important later on. So essentially, what's happening is that we install the iodine cell in the front end. Well, this is what we call the front end of the telescope, and that front end is itself mounted onto right underneath the bottom of the primary of the Tillinghast. And then ideally, once we have the iodine cell, we'll be able to take this superposed reference and stellar spectra and feed it through the fibers back into the spectrometer room. Obviously, I can't show you the spectrometer room because Dr. Fourier, who's the designer of trace, along with Dr. Zangiorgi, would probably not be very happy. So in more detail, this is how the iodine cell looks inside the front end. This is how it looked once we fitted it. And you will notice that there are iodine cell railings. And this is particularly important in the design because we want to be able to change the configuration. One thing that I didn't mention before is that one of the shortcomings of this iodine cell method is that this is a gas, and therefore once the stellar beam goes through the iodine chamber, we will lose approximately a factor of 2 of the incoming light, and therefore the sensitivity of the telescope will decrease. And because trace works at a very specific sensitivity limit, so the limit in magnitude of trace currently is 14 magnitudes, and that requires approximately an hour time of exposure. So if we decrease sensitivity, we would be hampering the current science ability of trace, but we can avoid this by using an iodine cell that can freely move into and out of the way of the stellar beam. The second part of my project included improving the insulation of the front end of the Tillinghast telescope. And right now, the insulation consists of these 2 green foam chambers, these 2 green pieces of foam. And the reason why we must improve the insulation is because once the iodine cell is installed, kind of over here, we will have a huge temperature differential between the dome and where the iodine cell is. As I mentioned before, iodine has to be kept at a very stable 50 degrees Celsius. And this is because we want to keep the iodine at a gaseous phase, and also because we don't want any shifts in the iodine lines. And furthermore, the dome has to be kept at a very stable room temperature because we want to protect the seeing of the telescope. So this is how my first model of the insulation box looks like. I first modeled it on using SolidWorks, and then I reproduced it in the lab. And I went back to Arizona and performed the first fitting of the insulation box, and it actually went extremely well, more than I was planning that it would go. The design works pretty well, except for the back, so I had to adjust it, and I have a new insulation box model. This is a mistake of mine, but this is essentially what it's going to look like. So now the next immediate step is to select actually what material we're going to use in building this new prototype. So I paired up with James Conaster, who's an engineering junior at the college, and he's very interested in material science, and he suggested polyurethane foam, which is a highly resilient material, and it has a thermal conductivity of about 20 watts per meter Kelvin, which means that it's about the same thermal conductivity as air. And it's more than wood and it's more than metal, so it could be useful in this design. But of course, I'm not yet set on what material to utilize. So the immediate next steps are going to be selecting the material for the insulation box, assembling the iodine cell in the lab, and continue working on the development of a software package to model the iodine observations. In the long term, we hope that the iodine cell will help us provide longer-term stability in radial velocity measurements, which will allow for detection of planets orbiting rival stars, amongst other science goals. And perhaps most importantly, will allow us to do more in-house spectroscopy of other targets, and as such, relieve time in Keck, HARPS, and the Hubble Everly telescope. This is a highly collaborative project. I got a lot of advice and help from many people. All of the people are listed here. Thank you very much. Does anyone have any questions?
I'm only vaguely familiar with measurements, you're passing it through the gas, so obviously that changes the spectrum that you're recording.
Correct.
And presumably you have to have a good sense of what that looks like beforehand to subtract it out.
Yes.
So you model it, you get the velocity information, then you subtract that out from the spectrum. Is that correct? Is that what you're?
Yes, that would be the goal of the software package. Because you are correct that when you impose an iodine spectrum, because there are so many features, you need a very
That are coming together.
exactly you need a very computationally heavy package to be able to subtract the actual observed spectrum from the superposition.
But you want to go to that effort because you're going to be able to increase your velocity since there's, like you said, by an order of magnitude.
Yes, by an order of magnitude. So the goal of the project, it's funny because in iodine cell projects, I've noticed that it's always from 20 meters, from some number to 1 meter per second. But the thing is that in order to get to 1 meter per second, for example, from 20 meters per second, you'd have to have 20 to the 2 more photons hitting your telescope. So you need a way brighter targets. So that is perhaps, so we still don't know if we'll actually be able to reach 1 meter per second. But that's the reason why I say 1 order of magnitude. Any other questions?
So you built that. Well, where did you, not that, but the box?
Oh, yeah.
When did you do the installation run?
Last week. I was in Arizona all week last week.
How did you design the box without first taking measurements of the whole back end of the telescope?
Oh, I did take measurements of this
So
front
you did
end.
2 trips? Or-
Yes, I did. Yeah, so I did the first trip, which was the fitting trip, just like of the cell, and then the next trip was the actual fitting, which happened last week.
And then there's going to be a model, you're going to cut the metal you have, or you're going to build a new box?
Right. So I destroyed the new box because so what I did was I literally jumped. I put the box in and I started making a bunch of measurements, and then to bring it back, it was just easier to break the whole thing. So I have to build a new cell, a new iodine box. Sorry.
And are you planning to go out and install that?
Yeah. So this is like an ongoing project. I'll certainly stay involved. So yeah, next time I will be fitting the new prototype. Hopefully, I still don't know if we'll be using the material that I mentioned on the next building of the next installation box, but I will be performing several more fittings before setting on the last material. Okay.
So is iodine cell like in place now?
No, the iodine cell's here in a lab at the CFA. We still have to be able to talk to the controller that allows us to, like a stage controller that allows us to move the iodine between configurations. So that's like the next step. So this is like, we're talking about a year from now at least for the installation of the actual cell into the telescope. Mm-hmm.
And then who's handling the software for that?
I'd have to talk to Professor Johnson before answering that question.
Might you be involved? Or-
Yes. Mm-hmm. Certainly.
Okay.
Yeah.
Very exciting. Many of us are big users of the Spectra.
Yep. Mm-hmm.
Okay.
Cool.
Great.
I'd just like to comment that you did this without breaking it. That's the
Yeah.
He was having a heart attack.
Yeah. Yesterday I was talking to Dr. Latham, who's one of the biggest users of trays, and when he saw these pictures of my fitting, he was very, very terrified that I had ruined something. But I was there the night after we installed. I was right next to Gil, who's the observer, the observer for trace, the main observer anyways. And I was there just to make sure that the telescope was running correctly. So, and I'm still alive, so I think that's a good sign.
I want to commend you on this because, having taught this course many times,
Mm-hmm.
hardware projects are really tough to fit into a 1 semester when, as Andy said, in reality, we only have about 8 weeks of the actual research.
Mm-hmm.
So it's actually neat that you got out to the telescope and did get some hardware.
Yep.
Okay, great. Well, let's thank you again.
Thank you.
Okay, now a very important announcement while we change the microphones, which is Penn Curly arranged for cookies and hot cider. So please
Okay, Jim. How is it a while?
Testing.
Yep, it's on. Okay. Usually I hear the sound of it. Oh, there you go.
Let me see.
Second one. This is going to confuse me.
So there's laser pointer.
Yeah, that's mine. So I brought it in.
Did you?
Yeah.
I thought you had left one.
I brought it in two. So I have, my sky observing laser, then the regular PowerPoint.
You own two.
Yeah. I mean, isn't it like a tool of the trade in a way?
Well, you've been doing astronomy longer than most. Okay. All right, we're going to get going. So the next speaker is Jimmy Castaño, and Jimmy is going to tell us about formaldehyde temperature modeling in the cloud in the central molecular zone. Okay? All right, so I'll give you a warning in 2 minutes, Jimmy.
Okay, let's do it. Okay, good afternoon, everyone. I'm here to talk about my research project on finding temperatures in the central molecular zone. For those of you unaware, this is the 500 parsec radius from the center of our own galaxy. I'm going to start out with an outline. That's what I'm going to talk about today. First, I'm going to outline some of the motivations for this project. Then I'm going to walk you through the data and the approaches I use to find these temperatures. And the last 2 points here are just the two different approaches I'm going to use. So I'll go into more detail of those later. So let's start with the problem. We find out that pretty much 80% of the dense gas in the Milky Way belongs in the CMZ, but only about 5 to 10% of the star formation happens there. That's kind of odd because usually we have an idea of star formation occurring with cold, dense gas, and the more dense and cold gas you have in the area, the more stars you have, but there's so little of it. So perhaps a problem that we're seeing here is that temperatures in these gas clouds just aren't low like we think they would be. So one question you want to use is like, why don't we use formaldehyde gas to find out? And then the question arises, why formaldehyde? So there's already been work in this area used before. So Ginsberg et al., Adam Ginsberg is one of my advisors on this project. He published a paper this year on single-dish data using the APEX telescope. Here we're using the SMA, the sub-millimeter array, located in Mauna Kea, Hawaii, to use it gets a higher resolution data on the CMZ clouds. You can also compare it to ammonia data taken on the CMZ. It fills in some of the holes that the ammonia surveys left behind. And just like CO, formaldehyde is a tracer of cold, dense gas. And this is more of like a convenience for observational purposes. It turns out that the two line transitions I'm going to look at today are quite close to each other in the frequency axis, so you won't have to rearrange the different arrays in order to get the same observation. So to orient oneself with what cloud I'm talking about, this is the map of the entire CMZ. Kara Battersby provided me with this map that she provides with the SMA legacy survey she's conducting. The cloud I'm looking at is one of the three little pigs clouds over here. And the explanation to the story goes just like the folktale. You have these three clouds that are quite similar, and they vary in the kind of structure you find. So you have the straw house with very little structure, then moves on to the sticks, and the bricks with the hardest structure. I'm focusing more on the bricks cloud in this project because I feel like with the higher emission lines, you might find more interesting results with this. And if I can make it work for this complicated cloud, I can make it work for the less complicated clouds. So walking through the approach, I made up this flow chart. Essentially, I'm looking at two different methods. So the first thing we got to do is look at two rotational transitions of formaldehyde, labeled 303 and 321 for short, up here. So once I get that, I try to fit a Gaussian curve to the emissions and record things like what's the width of this Gaussian, what's the center, and what's the amplitude most of all. Then the approaches start to diverge into two branches. One approach I use is what's known as a rotational energy diagram method. It basically uses radiative transfer and excitation temperatures derived from the Planck function in order to find sort of line populations of the formaldehyde gas in these clouds.
what you do here is that I take the fits up here and I integrate the fit and multiply that by certain constants related to the transitions I'm looking at. And eventually I'll get to temperature that way. Then on the other side, I have a tabulated radix model offered by my other advisor, Adam Ginsberg, which looks at collisional and radiative transfer in a sort of balancing act. And it's all tabulated with different parameters. And what it takes in as its main input is the ratio of the amplitudes. So here I take two separate amplitudes, and here I take the ratio of both of them. And the goal, of course, is to compare. So the setup here is I provide an example of what the cube looks like. So essentially we have a spatial axis, x and y, and then down the frequency or velocity range if you use the Doppler shift equation. And then inside each sort of pixel is a value for flux. So here's an example of the fitter I use. And I have two different data cubes that represent the two different lines. It's just two different regimes of frequency very close to each other, about 2.18 gigahertz. And the fitter works by, it's actually an interactive fitter in a way, because you can have a fit occur at each pixel because you have emission lines. And what it does is essentially it takes in a guess for center and width and amplitude, perturbs these guesses and computes a chi-squared, and it keeps perturbing those guesses until it finds a minimum chi-squared, and that's their fit. Eventually, you end up with a cube identical to the original, except that it's instead of just fluxes, you have sort of like the fitted parameters. And that's what I use for my observables. The real issue here was actually getting the fitter to work for the cube. So a lot of work had to be done with smoothing the data and also regridding it so that the signal and noise can be increased, and also for the fitter to run a bit faster. So before I talk more about the models, this diagram helps explain what sort of density regimes I can use the models in. So I mentioned the rotational energy diagram and also the radix. This is kind of where they lie on this diagram. The way to explain this is really thinking about the way you get line populations of a gas, like a transition, is really based on the density of the gas you're talking about. So there lies this whole range, and one must talk about the two extremes. So in a very low density environment, one would expect too many collisions to occur. So a lot of the line populations are governed by photon excitation. And at the lowest value, you get the photons from the CMB, and it ranges from there. And on the flip side, when you have very high density, you have a lot of collisions occur. This is kind of what we imagine to happen in the CMZ, where there's so much dense gas. So it's very extreme. We have local thermodynamic equilibrium, but that's at a certain density range that we don't find in these clouds. So it's somewhere in the middle. And that's what this curve kind of represents. It's a transition between those two extremes. It's divided by the end critical, so this is kind of showing like this is where both photon excitation and collisional excitation occur kind of at the same rate. So with one approach is the temperature estimate using rotational energy diagram. By equating equations from radiative transfer, that's where I get the use of column density and for the line profiles that I get from my observables. And I compare that with Planck distributions for these transitions to try to get the excitation temperature associated. Eventually, it comes down to this linear relationship between the population of the line, and also it relates to the excitation temperature and the energy of the transition. So here's where the observables come into play. We derive this here. So this is what the energy, you plug that in here. The observable is the integrated amplitude of the Gaussian. It's labeled as TeV. That's only because it starts out as flux, but one can convert it using the Planck distribution into excitation, like that, not brightness temperatures, not excitation temperatures. So using that and using two different points or two different fits, one can find 2 points on this line and then eventually get the slope of it, which is what we're looking for, which is excitation temperature. Sadly, though, I'm still not really able to get this temperature working. There must be something wrong with some of the values I'm using here. So one example would be like the values here would be like the Boltzmann constant, one knows Planck constant. Here's the spontaneous de-excitation rate of formaldehyde. I'm missing a G. Oh, no, here's a G. So this is also the degeneracy of the state, which is also quite debatable from the literature I'm looking at. So there's more to be done on this aspect, and I'll get back to you with this. But we lead with the radix result. I'm showing this first because this is how the cube looks like when not undergoing the fitter. You have bright emissions on this location right here, so I want you to just kind of focus on where the emissions really lie. The radix result is so. To be honest, in starting this project, I kind of imagined there being a certain temperature estimate for each pixel, but the reality of the situation is the second line that I'm looking at, the 321 line, is a lot lower than one would expect, and actually like messes up the tabulated models. What radix does is that it looks at H2 in the CMZ colliding with formaldehyde, and the temperature of the H2 and the velocity of the H2 give a sense of just how many collisions are happening. And it tries to balance that with radius transfer within the cloud in order to get a temperature estimate. So my results here are that I get temperatures in between 150 to 280 Kelvin. And that's actually quite high. It's not too unreasonable because work done by Adam Ginsberg leaded to things like 40 Kelvin to 100 Kelvin. So it's a bit higher than before. So what do we get from this? Points to higher temperatures, so it kind of answers the question that, okay, maybe the reason why there's not so much star formation in this region is because the temperature is too high. It also gives us insight into star formation in the centers of other galaxies or distant galaxies who the galaxy themselves are kind of like our CMZ. And also the method I used here, the automatic fitter, and the way I can plug that into radix is applicable to the entire CMZ eventually. Here's my acknowledgements. That's all I have. Thank you. Okay, let's hear them.
Okay, now we have a request from one of the online viewers that the speakers please repeat the questions.
Okay.
Because only you were live.
It's good.
Which also means that the online thing is working. All right, questions?
I have a very simple question. Do you know what the dust temperatures are in the same region that you're looking at?
Okay, so the question was, do I know the dust temperatures? I do. It was given in the Ginsberg paper, so that was used in the radix model.
Oh, 20?
Yeah.
Yeah, so, yeah, okay, crazy. So how likely do you think it is that really you're at like 200 in the gas and 20 in the dust?
I mean, it kind of goes against a lot of what I've been taught here. But, I mean, this is research after all. It's kind of cutting edge in a way. That's why I'm really hoping for that other method to pull through so that I can compare those results and see if I can believe it or not.
The formaldehyde on like large scale is like hundreds of pounds.
Okay, other questions?
Yes.
Just one in the back. Can you flip back to the temperature color plot?
Sure.
I don't quite understand how you get temperatures on spatial scales that seem higher resolution than the underlying point spread function of the intensity map underneath it.
That might be in. Yes, I think so.
But when we were loading up your presentation, you said that the black and white image was much blurred.
Yeah. So this is kind of like a PowerPoint issue that I'm encountering.
Is that really the answer? I mean, I don't mean
It is. If you were to look at my screen, they kind of fit better.
Why? Sorry. So why is there not temperature estimate throughout? Why are there only these patches? I just missed that.
Right. So.
Repeat that. Sorry.
Right. So the question was why do we only get temperature estimates for just small patches? First of all, I also like to point out that the white patches you see, they kind of point to like really high temperatures. What it's really pointing at is 350 Kelvin, and I actually throw those away because that's supposed to be the limit of the radix model. So that just happens because so I'm taking the ratio of amplitudes for the two different maps. And sometimes the ratio for the second transition line just isn't high enough. So if it's not high enough, like just completely like very, very low, it won't give us an estimate. And if it's just barely, that it fits the edges in the model, it'll give us that sort of edge estimate there. So these are the more reliable numbers here. It's just because it kind of relates back to where you see most of like the emission. Mind you, this is also like a slice of one of the two cubes. So there are several different slices, and there's two cubes in mine. So maybe I could have presented that a bit better. Andrew, you had a question? Okay.
But could it be that the temperature is actually colder and you only see it in the places where does a hotter temperature produce stronger lines and therefore higher signal to noise?
That's what I'm finding, it seems. It's still under debate. I'm trying to figure out why.
Okay. Well, I have one final question, which is, you started off saying we don't understand why there isn't star formation here, and then you ended by saying I measured a high temperature high enough to preclude star formation. So that seemed really interesting. But then are you saying that you really don't believe those temperatures, or are you saying that you think you might have solved this mystery?
I believe this is...
Oh, I'm sorry.
Right. So the repeat of the question was, I started out saying there's a problem with the CMZ, that we don't really understand why star formation isn't happening as much as it should. But then I try to conclude saying that, okay, this is probably a reason. I think this is just like one step in the dialogue. So this is one answer I have. There's still definitely a lot more work to be done, but I think it kind of starts the discussion.
All right. Any final questions? Okay. Thank you. All right. Sorry, I'm going to stick in here. You guys can figure out that.
Yeah, just like belt loop.
So, how do you want to do this?
Should I just...
You can pop out of it and pop back in.
Yeah, that's what I think we'll do.
You can also try embedding it right now.
That could work.
So, do you want to do that?
Yeah,
So,
sure.
is that you?
I think that one doesn't.
And then see if you can embed it right now. If that's, was it long to embed last time?
I don't think so.
Okay, so try it. Just take a minute. If not, then you can just come out to the desktop.
Okay, I'll add a new slide. And then, oh, that's a new PowerPoint. No, okay.
Yeah, if you just delete that image. And then
Oh, I see, okay.
do you want to, yeah.
That. When clicked. Okay, let's, I guess if it works then, and if it doesn't, I'll just go back and
Very
look
true.
at that.
Do you want the presenter tools?
Yes, please.
Yeah, so just go to slideshow and take the second option.
Okay.
Okay, great. All right, our next presenter is Matthew Pasquini. He's going to tell us about the catalog and properties of local molecular clouds.
Okay.
Okay.
All right, yes, so my work this semester in Astro 98 was on making a catalog and collecting the properties of 31 local molecular clouds. So a bit of background. So molecular clouds in the interstellar medium, ISM, are important star-forming regions. So it's useful to know both their individual properties as well as their collective properties, such as their mass spectrum. So there does exist a very extensive catalog of molecular clouds throughout the Milky Way, as you can see here. That was generated by Rice et al. In 2015. And they used a carbon monoxide emission map and a dendrogram, and they used a dendrogram on this map. A dendrogram is a tree diagram that identifies the hierarchical structure of this map according to its intensity of the emission. And they derived the position of each of these features in the dendrogram from a rotation curve by translating its relative velocity with respect to the sun into a distance. And so they used all that data to collect a catalog of around 1,000 molecular clouds throughout the Milky Way. One problem with the study was that it wasn't able to fill in, pointer, this one spot here with the clouds because the relative velocities of the clouds near the sun are too low to resolve a position from them. And so what this study does is I use new distance data that comes from a study last year by Schlafly et al. That uses photometry to measure distances to dust features in these clouds at very low uncertainties. So here's an example of a bit of the data reduction process. So this green line outlines a feature in the dendrogram that corresponds to a feature in the CO emission that I call a molecular cloud. And these purple dots here represent the distance data that I pull from the Schlafly et al. Catalog, and I overlay them together to kind of by hand pick out which distance data correspond to which
features in the molecular, in the CO emission map. And I use that to create my catalog. And here's another example of the Cepheus region where I pull out a number of features from the dendrogram and associate them with different distance points to get a very nice dissection of larger regions like this one. So what might have previously been called a single molecular cloud is actually made up of individual pieces that are actually up to an order of magnitude in terms of distance from each other. So it's a very kind of nuanced sampling of a very large system of clouds. And you can see on the right here, and it's true for the previous plot too, that in velocity space, this feature is not none of these features are very well resolved in velocity space, which is the motivation as to why we want to use the distance data here. So you can see that kind of in action. So the data reduction process is as follows. So there's the first category of properties is the observational properties. So things like latitude, longitude, the angular size and flux of the clouds, which you can compute which I computed directly from the dendrogram, as well as the distances that I pulled from the Schlafly et al. Catalog. The second category of properties is the physical properties of the clouds themselves, like their radius, their luminosities, their mass, and their galactic radii. Importantly, the mass is actually computed directly from the luminosity. I found that to be the most effective method of determining their mass when comparing to a few known masses from recent literature sources. And here's an example of some of the data I've collected. So there's 31 clouds total, but here's a sampling of the first 10 for both the observational and the physical properties. And so here, as long as the technical stuff works. Oh, I guess not. All right. So I will pull up the video. So I made a visualization in Worldwide Telescope of this data. So let's see. Okay, great. And so all these purple dots here. Oh, okay. There's some music. So all these purple dots here represent the clouds from the dendrogram from the Rice et al. Catalog. And you can see how there's this missing region in here near the sun. So we plot then the distances to the dust features from the Schlafly et al. Catalog, and then zoom in on the solar region here. All right, so here's the solar system, and then, so looking out into the sky, like looking out into that emission map, I then plot the clouds that I put together from that process that I showed you a couple slides back. And just kind of scan the sky a little bit. All these green dots are the clouds that I picked out and cataloged and found their properties. And then you can zoom out, and you can see where these clouds lie in the context of the existing catalog. You can see how it kind of fills in that hole quite nicely there. So it kind of completes the catalog with a very nuanced look at the local clouds. Okay, so that's that. Sorry. Okay, so I want to talk as well about some of the sources of uncertainty involved here. So one major source of uncertainty is the uncertainty in a factor that's called XCO, which is basically a linear translation between the intensity of the carbon monoxide emission and the column density of the H2. And so that's important in calculating luminosity and mass, or just mass rather. And there's also uncertainties that come from the Schlafly et al. Catalog in the distances that are an average of 7% statistical and 10% systematic, which, although important, are definitely a very, very good improvement in this distance resolution that we've had from previous literature sources. For a limited angular dynamic range, which is what we'd expect for a map in L and B coordinates, we should have that the mass that we can observe is limited by the radius of the cloud squared, as we see here, and that the mass is also limited by the distance of the distance to the cloud squared. And so, because we see both of these trends in both the galaxy-wide and the local catalog, we've ruled out any additional biases from being present. So we actually have basically as good resolution, as good of a detection rate for faraway clouds as we can have.
So I also compute a mass spectrum for the local catalog. Unfortunately, there aren't really enough clouds to really make a statistically significant catalog because we only have 31 clouds. But their distribution does correspond to the distribution in the Rice et al. Catalog in the outer galaxy, which is defined to be beyond the solar circle. So that's that. I also plotted a few distributions between the two catalogs. Of course, with a distance distribution, most of the clouds in the local catalog should be closer than the clouds in the Rice et al. Catalog, which is what we see. For mass, they correspond quite nicely for the most part, the exception being these clouds over here, because in the local catalog, we're actually able to resolve much smaller clouds that were not able to be resolved in the Rice catalog. Column density matches up nicely between the two catalogs, and of course, distance from the galactic center. In the local catalog, you see that they're very much concentrated around the sun, which is what we'd expect. There's one interesting thing I found in the catalog too, is that the vast majority of the clouds in the catalog were actually present outside of the solar circle. And there are two possibilities that explain this. One possibility is that this is a representation of the Orion spur arm, so basically a large chunk of molecular clouds that sits right outside the solar circle in the nearby region, as kind of an indicator of an underlying large-scale structure that doesn't exist closer to the galactic center with respect to the sun. The other possibility is that this is just an artifact of the data because the Schlafly et al. Catalog focused away from the galactic center. That's also another possibility. So it's not entirely conclusive that represents the Orion spur arm, but it's noteworthy nonetheless. So some of the conclusions. So we have a catalog here of 31 local molecular clouds and their properties. The cloud distributions are in agreement with Rice et al. 2015 catalog. The local and galaxy-wide catalogs are consistent with sensitivity limits. And so because of these two catalogs being in agreement, it's a union of vastly different methods of determining distances to these clouds and therefore their properties. Some improvements that might be possible are a higher angular resolution in the CO map, as well as more targeted distance data, such that we have more photometric distance data applied to regions that would be of interest that you can simply read off from the dendrogram, so you can kind of have a more targeted correlation between the two data sets. One thing to mention is that, my apologies. So those two things could be improvements. I'd also like to acknowledge Dr. Alyssa Goodman, Tom Rice, Catherine Zucker, Dr. Cara Battersby, and of course, David Charbonneau and Astronomy 98 for their assistance in this project. Any questions? Yes.
Could you expand a bit on how you picked out these particular clouds, these 31 clouds, and what fraction of the local molecular gas do they represent?
Okay. Yes. So the question was how I picked out the molecular clouds and what fraction of the local catalog they represent. So I think it's worthwhile to look at plots like this one. So. And what's important about this catalog is it is certainly not a fully complete catalog of the local clouds. So as you can see, I was very much limited to clouds that had a correspondence between the Schlafly et al. Distance data and the CO dendrogram map. And so, for example, this feature right here didn't have any distances associated with it, and so I couldn't match up the dendrogram and the distance data there. And so it's certainly not complete as to what percentage of the local clouds I have in this catalog. That I actually don't know, but it's certainly not complete, and that's something important to point out.
So
yes.
basically, they had one distance data point if you used it.
Yes, for the most part, yes. As long as there was a correspondent, I used wherever there was a distance data, I used it to identify a cloud or multiple clouds.
Just to clarify, in the upper right corner where you have the dendrogram and you have many separate green features, that cloud on the left that looks like one thing, you made the point before that that's actually several things, right?
Yes, so the question was whether this blob of green stuff here represents more than one cloud, and the answer is yes, that this green stuff here corresponds to all these green features in the dendrogram. So it's a number of different features.
Tom's question, it's one pink dot per green feature.
Not necessarily. It's not necessarily one pink green dot per feature. Sometimes, for example, in the Perseus cluster, there was a very large number of distance data for a single dendrogram feature, and so, oh yes, at least one distance data datum per green feature. Yes. Another question, Tom?
So would you divide a single dendrogram feature into two if they had two different distances within it?
The question. Oh. Yep, so the question was whether I could divide a single feature in the dendrogram into multiple pieces for different data points if there were multiple distance data inside the same feature. The answer is no, and if I had different distance data inside the same feature, I usually average the data and adjusted their uncertainties accordingly. Yep, I didn't have any cases where it was one feature and very widely differing distances. Okay, other questions?
So I had a question. Just if you could. So what is the typical mass you think of these nearby clouds and their distance? I'm sorry if I missed it. Just to give me a feeling for what kind of range we're talking about here.
Right. So the question was, what is the typical mass of these clouds? And so as I said before, it's not really it's not particularly useful to give a very discrete answer to that question simply because it's such a limited data set. But you can see how most of the clouds fall somewhere between 10 to the 4 and 10 to the 5 solar masses for this catalog with a lot of outliers. Is that a sufficient answer?
Yeah, and there's some at a couple hundred parsecs?
Yep, most of them are within 100 to 1,000 parsecs, with some lying a little bit about 1,000 parsecs.
So are these among the very closest clouds that have been?
Yes.
Are they
Yes.
the closest?
That's a good question. I don't know if they would qualify for the superlative of being the closest, but they are a much closer sample than the Rice et al. Catalog.
Probably a few very close ones, because it's hard to get the best distances. But we should, Matt's going to keep working on this next one.
Oh.
Yes, indeed.
We'll answer your question about which ones don't have distance information and what fractions.
Okay.
All right. Other questions from that? All right. So if you could go and make one measurement, what would it be? You alluded to this at the end of your talk. What would be the one thing you do to really improve this in some reasonable observing program? Not something that could never be done.
Basically, so if I could do one additional measurement, I would like to repeat the Schlafly et al. Photometric distance survey, but choosing the coordinates based on the CO dendrogram, so I can basically match up more features.
Yeah, great.
Do I have time for one more question? Or okay, yep.
It's actually just a comment. You should talk to Doug Finkbeiner because they actually have an online tool where you can put in coordinates and actually get a statistical extinction map along that line of sight. So
Okay.
you can go that way around.
And he might have just watched your talk because he's listening online. Okay, great. Well, let's thank Matt again. Charles is up next.
Mine was the one.
Is it in the browser?
It's in the browser. It's like the last tab.
After yours, I'm going to turn off the wireless because I'm worried we're going to get some bizarre text. All right. Which one was it? The last one?
Yeah, I think it was the last one. That one.
Okay, very good. So as
I got it.
Okay, all right. So our next speaker is Charles Law. Charles is going to talk about searching for temporal variations in diffuse interstellar bands. Okay.
All right, so my project was working on temporal variations in these dibbed bands in the spectra of core collapsed supernova progenitor stars. All right, some background. Diffuse interstellar bands, often called DIBs, represent over 500 plus absorption features in the near infrared and optical spectra of massive stars. The sources of these features are often called carriers, and they're believed to be polyatomic organic molecules. However, the central wavelengths of these features don't correspond with electric transitions of any known atomic or molecular species. They're believed to be located in interstellar regions, and as such, they shouldn't change over time. But there's previous literature that suggests some temporal variability of DIBs in the circumstellar shells of stars. Just for some visualization, here's a plot of a bunch of these DIBs features. And two things to note of this is how numerous these features actually are, and also how strong they are. There's been almost it's been a century since we've discovered these, and there's been a lot of theoretical, experimental, and observational work, but we still really don't know what these features are. All right, so some of the work that prompted this project was there's evidence of interaction between the supernova 2012 AP, which is a type 1c broadline supernova, and the DIB carriers. You can see in the plot on the right is evidence for a DIB at 6,283 angstroms. Its equivalent width is changing in time over a relatively short time scale, maybe 25, 30 days. This happened for several DIBs. It was observed, and this is actually the first time this was the equivalent width changing in DIBs was observed in an extragalactic object. This suggests that the carriers may be located in the circumstellar shells of some of these stars, and that the supernova blast is interacting with these carriers and causing these changes. Interestingly, the archive search found two other cases of time-varying DIBs, or potential cases of time-varying DIBs, in spectroscopically similar supernovae. So I worked on a stellar sample of 16 massive stars that were thought to be progenitors for supernova type 1 BC. These were mass-losing stars with enhanced oxygen and nitrogen-rich environments. This is because there's previous literature that suggests DIB time variation in these stars with these particular types of environments. The data that I worked with, taken with the trace Echelon spectrograph, it's a high spectral resolution, and our wavelength range that we were most sensitive to was 5,000 angstroms and up. I worked with about 50 observations between June and November of 2013. Our typical signal-to-noise range from 5 to 15. So we resolved DIBs at 5,784 angstroms, 5,797 angstroms, and 6,283 angstroms. Unfortunately, I was unable to resolve the DIB at 4,428. This was seen to change in the supernova 2012 AP, but the data here were not strong enough to pick out this feature. So what I did was heliocentrically corrected these spectra and continuum normalized them. And then for the DIB features, I used a Gaussian fit to model to analyze these features. Gaussian, doesn't fit it perfectly, but it's a good first-order approximation to look for time variations in either the equivalent width or the radial velocity. And one might be worried about the robustness of measuring substructure in our features. And so here's a representative plot of a DIB at 5,797 angstroms. And you can see that this is our data, and this is the data from a paper that used a spectrograph with a spectral resolution of over 100,000. And you can still see the substructural features corresponding in our data and in their data. So I feel confident to talk about the substructural changes that we see in these features. Okay, so no measurable change was found in 13 out of 16 of the stars. Here's an example of one of the stars that didn't show any change, MT83. So looking at principally these three DIB features, you can see the equivalent width over the observation periods stayed very constant, and the same thing with the equivalent width of this DIB at 6,283, all within error bars. We didn't see any significant change here. So now on to the more interesting candidates. So the first candidate for change was MT59, which is a massive O-type star in the Cygnus OB association. So it's best shown with animation. So this is the first epoch. On the left is going to be several epochs, and I'm going to scroll through animations. And so here's the first epoch. And then looking at a second epoch, we see slight appearance of these features in both DIBs. So there's this sort of this feature that appears right here that we don't see in the black, and there's this feature that appears here that you don't see in the black either. And this is after 7 days of time. And then going on to the next feature, it sort of disappears. It's kind of hard to see, but the blue is another day after this. So this is really on the time scale. If you can see here, the time scale is really quite quick. It's a day change. And you can see the changes in the graphs here. The next potential candidate is a Wolf-Rayet 2. This is a Wolf-Rayet star, subtype nitrogen Wolf-Rayet star. Similarly, you can see the first epoch that we're dealing with is September 11th. And then the next epoch, you see this, basically the disappearance of this black substructural feature here, and in the red basically dips way down. There's also some features right here, this red, though I'm not 100% convinced about that reality of this. This is the feature that I believe more in. And then if you look at the blue, it sort of goes away again. And basically, you can see that you don't really see changes much in the equivalent width, but the changes are seen when we're looking at the radial velocity. The radial velocities were determined by just taking the central wavelength, the minimum value of the Gaussian for fitting the central wavelengths. And this doesn't necessarily imply that the central wavelength of the DIB feature is changing. This just means that possibly some substructural feature appeared that changed the Gaussian fit, and that's kind of being seen here. So changes in the radial velocity of these measurements are often good indicators for some potential appearance or disappearance of substructure between epochs. The last candidate was a white giant and luminous blue variable. And so this was for the DIB at 6,283 angstroms, which is particularly difficult due to contamination by telluric features and the fact that it's at the edge, the left-hand side of the echelon order that we're dealing with. So it's very hard to get accurate measurements of the radial velocity and the equivalent width. So this is more of a visual inspection. This is just making sure that we're aligned, looking at the same area, lining up some of the telluric features. And then the feature that potentially is changing is this right here, how the red, this is a difference, 60 days difference between these observations. And the change occurs right here potentially, in that the black sort of goes like this, and the red comes down. And there's this plateau that appears. Okay, so we have some evidence in these from these previous plots. There's some evidence of stellar-wind interaction, and that the carrier material may be located in the circumstellar shells of these stars, and the interactions that we're seeing between they could be explained by interactions between the star and the DIB carriers. And note that also the changes that we see are not uniform across features or stars. It's possible that there is a chance alignment with distant clouds that have DIB-rich material in them, and they're just passing in front of the stars, and that's what I'm seeing. However, it's possible to constrain the size of these clouds based on the timescales of the variation. And you can do this, and you get clouds in the order quite small, 10 to the -5th, 10 to the -7th parsecs. If you assume, assuming for, to put a constraint, the velocity of maybe 1,000 kilometers per second of high velocity clouds. And there's really, this has to be the most wispy kind of small clouds, and they don't really generally travel at that kind of speed. So it's probably not this, but it's definitely something to take into account. It's encouraging that we see changes, especially in the MT59. We saw changes in both of these DIB features. The intensity ratio between the DIB at 5,780 and 5,797 angstroms, this intensity ratio correlates with molecular column densities. And so that means this ratio says something about the physical carrier environment. And so it's encouraging that if we see the changes in both of those. Could mean that the physical carrier environment is changing due to interactions with the star. The star erupting or something, winds. So I measured the H alpha radial velocity in a similar Gaussian method, and it did change. The changes in the H alpha emission in the star MT59 did correspond with the DIB changes in equivalent width and radial velocity. But to really make some more conclusive statements, I need to look for any substructural changes. If I can see any substructural changes in the H alpha emission in this star, something that needs to be done next or looked into. So I have identified 3 out of 16 stars have potential DIB variations. But really, to confirm the validity of the appearance of this substructure and the change with time, you really need a larger survey with a higher signal-to-noise, 100 or greater, because we were dealing with 5 to 15. And it's very possible that we're getting that these results, they're suggestive, but they're nothing conclusive yet. But the suggestive nature of them does challenge the current belief that all DIBs are created in the ISM. And so this is possibly establishing or possible evidence for an alternative production pathway for some DIBs being created in the circumstellar shells of stars. because the ISM is replenished by the circumstellar shells of a bunch of stars. So it's reasonable to assume that some DIBS carriers are located here. And so if this is the case, and if we can find, with a larger survey with a higher signal to noise, if we can find more cases of these, it could be a unique way to probe the physical properties of these DIBS, especially since it's not that still after so many years, we don't really quite understand them yet. And I want to thank my mentor, Professor Charbonneau, and all of Astro 98. Questions?
All right.
Yeah, so based on how many DIBS there are and how many you've seen that seem to vary, like how many DIBS do you think out of the ones that you know exist may actually vary on significant time scales?
Okay, the question was, considering that we have there's lots of DIBS, then seeing that there's some change in these couple, how many would you expect to see? And I don't know. That's an open question. This is the first time that there's any suggestive evidence, or one of the first cases of suggestive evidence of time-changing DIBS. And that the results from the previous supernova was the first time that had been seen in an extragalactic object. So that's an open question. There could be a lot. There could be only a few. We don't know yet. That's hopefully what, a larger survey, if it finds more, then we find that some of the other ones are changing in these particular types of stars, and we could use that to probe them. But it's possible that only like a very specific small family of DIBS changes because their particular carriers are created in these types of star environments.
I was just wondering what other surveys that are coming up might have the resolution and sensitivity that you need to get a big sample.
So the question was if there's any other surveys that I know that are coming up to do this, and I don't actually know the answer to your question. What would be what survey we would need if there is a pre-existing one coming up that we could use the data from?
Which one?
Okay, interesting.
Yeah, I don't know if there's any DIBS in the H band. I can't remember, but if there are, then Apogee has 100,000 stars, each of which have been observed 3 times. Now, most of them are not the type of star forming star you're looking for, but some of them are. So there might be useful data there.
Okay, well, thank you.
So were these spectra gathered for this purpose?
Yes.
So why did they pick the cadence they did? Why were they looking for such short timescale variations?
Oh, well, we saw the short timescale variations would imply that. Oh, sorry. The question: why was the observational cadence set that we were looking for short timescale variation? There's the previous supernova result did show short timescale variation, and also if you expect like stellar winds interacting with the DIB carriers, you'd expect it to be on relatively short timescales because say that something in the star happened, and like erupted or hit the circumstellar shell. This wouldn't happen over necessarily huge timescales. You could see changes over large timescales too, but there's this evidence is for relatively. We do see some changes over short timescales. The stars were picked survey-wise because there's previous evidence for the change. There's a couple of papers in the past that hypothesized there might be changes in the circumstellar shell, DIBS in circumstellar shells, for enhanced oxygen and nitrogen-rich environments.
So if the lines aren't really changing, if they are changing, great. If they're not changing, then what's the cause?
If they're not changing, then the DIB carriers wouldn't be located in the circumstellar shells. They'd just be out in the ISM.
I see things changing in your data. So if they're not actually astrophysical in nature, is there
I would say
the instrument or is it the
noise.
atmosphere?
Probably noise, or that's possible. But probably noise. We're mistaking noise for substructural features.
What source of noise do you think?
Probably instrument. Yeah, because we were pretty. We're signal noise 5, 10, 15. So it's possible that some, especially there's the concern that MT59 was pretty noisy in the data we see during this this epoch.
Yeah, I didn't like the fact that your variable spectrum was the noises.
Yeah, that is a concern, especially for MT59.
But
The other one is better, yeah. So that hopefully that's something real. But it's important that this is suggestive. I'm not saying like, oh, this is for sure. I see the changes. Yeah, the noise.
Comment. You got to start somewhere when we did this thing.
Oh, sure.
And, if you go back to one of your preliminary slides, I think this hammers the point home. We compare the data before to your data.
Which one?
Going back. There. So if we get spectra like you see it on the right, and you see changes there, that's undeniable, right? So we started with something on the left, and we see what we believe is changeable. It's real change because the trace is fairly stable, right? It's 3 sigma, etc. So if we can get, now that we see something, if we can get data like we see on the right, and that changes, and if we see changes with H alpha associated with clumping, that's a home run. And Charles refers to target.
Great. Okay, well, let's thank Charles again. Daniel is up next.
You can just close out.
All right. There you are. There you are. There's that laser pointer for that.
See.
Okay, so our next speaker is Daniel Chen. He's going to talk about predicting the guiding ability of LSST in poor weather conditions.
Right.
Okay.
Thanks. So I am working with an exploration of the LSST's ability to guide in poor weather conditions and while pointing to the region of the sky with the lowest stellar density. When I say poor weather condition, I can actually compare that to historical weather data taken from the site of the LSST. This is data taken from the Essence Supernova survey over 6 years of observations. And what they've done here is looked at the information from every single one of their images and found the magnitudes of cloud extinction that the images were observed through. And what this tells us is that for about 95% of the images that are taken there, there will be little to no cloud extinction to worry about. But for the remaining 5%, there's actually some significant cloud extinction. And so that's the question for this project is, can the LSST be guided in these worst weather conditions of 0.6 magnitudes of cloud extinction and above? And so why explore this worst case scenario? Well, when working on a project that takes about $40 million a year to operate, being able to optimize 1% of that time is already worth $400,000 per year. Furthermore, being able to use the LSST during these poor weather conditions means that we do get that extra 1% of data that could be important for studying transits or the sky. So this is what the focal plane of the LSST looks like. The blue part is the main science focal plane where the images are going to be taken. The 8 yellow boxes are the 8 guide sensors that I'll be talking about. And you can see that they're kind of grouped into pairs along each of the corners. I'm going to call this quadrants in this presentation. And in my program that I developed for this project, they are actually modeled as circles, even though they're actually squares. And there's several reasons for that, but the most important one is it's just much faster to compute that way. And for every time this focal plane points at a certain location, it actually can rotate to find the best configuration for which guide stars can be found. So if this points at a region and there are no guide stars for like this horizontal position, there's some degree of rotation up to 90 degrees, because after that it's kind of redundant because they overlap, where better guide stars will be found. And the width of the guide sensors and the arc that it travels across gives about 13 distinct orientations that I test in order to find the proportion of successful guidings for each field of view. And the 4 green boxes are the wavefront sensors, but I won't mention those until the very end. So the LSST will need to be constrained across these 3 degrees of freedom, the azimuthal and the elevation, like all telescopes, and then also the rotation. In order to constrain these 3 degrees of freedom, 2 guide stars are needed, and in order to achieve the highest possible precision in constraining those 3 degrees of freedom, the 2 guide stars need to be picked from 2 separate quadrants on the telescope. So here are the variables that decide whether or not a star can be considered a suitable guide star. Most trivially, the location. If I point at a certain field of view, the guide star has to be within one of the guide sensors areas of one of the guide sensors field of views. They also have to have a minimum brightness to achieve a signal to noise of 100, given a readout rate of 9 hertz and a readout time of 10 milliseconds. They have to be below a maximum brightness to avoid saturating the guide sensors. And one of the limitations of the LSST's kind of filter system is that the same filter that the LSST's science frame is looking at will also be applied to the guide sensors. And so this analysis is then, therefore has to be carried out for each of the wavebands that the LSST is interested in. I'm presenting the I band because it's kind of it's the center of the waveband region that the LSST is interested in, and it's also it also happens to be one of the most complete wavebands in the star catalog that I'm using. And then the last constraint is the guide stars need to be isolated from other similarly bright stars. But because I'm looking at the worst case weather conditions, I'm going to be looking for very bright stars, and those are rare enough that I don't actually have to worry about finding 2 of them in the same guide sensor, much less 2 of them close enough to interfere. And this is supported by star count models. Prior findings using the galactic star count model finds that while looking at regions with the lowest stellar density, which is the galactic North Pole, there will be about one 13th magnitude star per guide sensor. And I'm actually looking for stars brighter than that. So chances are I won't find stars that are close enough that I need to worry about the isolation constraint. So what I've done now is I'm actually taking this instrument and pointing it at kind of a theoretical or an actual star distribution. I'm pulling the stellar data from a NOMAD catalog, which is provided by the U.S. Naval Observatory, and it compiles 11 different star surveys together with information about multiple wavebands. This is a mock star distribution that I created for the purpose of explaining the process of selecting a guide star. The numbers across the bottom correspond to numbering of each of the guide sensors. And what each point means is if a point above guide camera 3 tells me that I found a star of that magnitude within the field of view of that guide sensor. And so for this kind of hypothetical process, I'm going to say that there's no saturation concern. And so I'm just looking for the brightest possible guide star. And so that happens to be in the guide camera 3. And so that's my first guide star. And then the second brightest is in guide camera 4. However, since, as I mentioned before, in order to achieve a high precision, I need them to come from 2 different quadrants. I can't use that one to guide, and so instead I look for the second one. And so this is what I would call a guiding success, because I found 2 guide stars that work. But this is because I didn't place any constraints on the magnitudes. And so now I'm going to place a constraint that I need to look for a magnitude 9 to 10 star in order to guide. And this actually corresponds to a condition where there are 3 magnitudes of cloud extinction. And so I'll be showing like the real result a little later. In this case, there's obviously only one bright star, and this is a failure because there's no way we can constrain all 3 degrees of freedom using just one guide star. And so this same process is applied to each of the proposed field of views for the LSST. And for each field of view, it's actually applied 13 times for each of the 13 rotations for which the instrument makes in order to look for these guide stars. And I evaluate the proportion of the successes for failures in order to find out how the guiding system will work under different weather conditions. And so it turns out that in normal weather conditions, the LSST can guide just fine. And that makes sense because presumably when they designed this, they wanted a telescope that worked. So there's no problem here. Under 1 magnitude of extinction, it's still fine, but already there are certain points, the lower 2 points, for example, where those would be recommended that you probably don't want to look at those 2 specific fields while suffering 1 magnitude of extinction. under 2 magnitudes of extinction, which occurs 1% of the time. Again, there's definitely several points where the LSST now probably shouldn't be looking at under these weather conditions, but there are also a lot of points that it still can look at. And kind of under even worse conditions that will happen 0.1% of the time, it becomes really, really difficult to guide. But my program actually will actually tell the LSST which specific field of view can be guided. So the main conclusion of that is, even in the worst weather condition, pointing at the region with the lowest stellar density, which is the galactic North Pole, guiding can still be carried out. And that's really good because that means we're using even 1% of the worst weather conditions. And so future work will hopefully expand this to more than the 20 degrees of magnitude, or 20 degrees of galactic latitude that I presented here. It will reintroduce that isolation constraint for completeness purposes. And by introducing that isolation constraint, I can also apply this to look for stars for the wavefront sensors that will control the adaptive optics of the system. And then I will create a program that will hopefully interface with the LSST directly, so it's actually going to be used there. Yeah. So I worked with Dr. Stubbs, and thank you to Astro98 and Professor Charbonneau. Questions?
Okay.
Yeah.
And don't forget to repeat the question.
Sure.
You, at your early slide, you mentioned that LSST also has a wavefront sensor.
Yes.
Presumably also has to have a bright star on it in order for LSST to stay in a good shape.
Yep.
So is that considered a concern for this?
So that will be considered a concern, and so that's so now I've shown that the guide system works, but now this could also be used and will probably be used to also find out whether or not the wavefront sensors find enough stars for each point. And that's just a simple matter of redrawing like where each of the sensors are being tested, and also reintroducing kind of the constraints that wavefront stars used for wavefront sensing require.
So you used a range of 1 magnitude for the faintest and brightest
Yeah.
stars that you can identify. Is it really that narrow?
So it's actually kind of fortuitous. It's not exactly 1 magnitude. It's like, I think it's like 1.2 or something when the math actually works out. So, but I was kind of surprised at how narrow it was. But I also just picked 1 for demonstrative purposes. But it is about like 1.2 or 1.3.
You may have mentioned this, and I may have missed it, but you talked about magnitude, but you talked about seeing. So if you have,
Sure.
sub-arc second seeing or 2 plus arc second seeing, it's limiting on your point as well.
Yeah. Oh, sorry. I didn't repeat the question. The question was about in reference to how seeing will also affect the guiding. I was specifically looking at like magnitudes due to cloud extinction. Taking into account seeing is probably something that also should be done, but I didn't do it here. And also, I think in our discussions we decided that seeing was less likely to be a concern than just having like clouds in the way.
Every LSST unit will be 0.4 arc seconds.
Oh, good.
Yeah.
Good, that's really
Or your money back.
Okay, great. Well, let's. And put the microphone up as high as you can on your tie.
Sounds good.
Stay within the bubble. So what do we decide?
So-
Did the animation work? After
Yeah,
you
I think it should. Worst case scenario, I'll just
pop out?
come back in.
Oh yeah, that's right. We put this one in. Okay.
All
There's
right,
a
great.
laser pointer if you like.
Perfect.
Okay. Next speaker is Ben Lee. Who's talking about probabilistic cataloging across crowded images, multiple bands.
Great, thank you very much. So yes, so my project is on probabilistic cataloging, and my mentor is Professor Doug Finkbeiner.
So of course the first question to address here is what exactly is probabilistic cataloging and why is it something we should be thinking about? Well, conventional cataloging software, given one image of a stellar field, will return one realization of a potential catalog with x and y positions, fluxes, and associated error values. And while these conventional methods tend to perform quite well on most images, they tend to fail in two limits. So first on the limit of very crowded stellar fields, and then also on the limit of detecting the faintest sources in the image. And so if we look here, this is just a sample DECAM image of the galactic center, and we just zoom in on a small portion of it, we can see why this becomes an issue, right? It's not clear as to how many sources are even in this image, what are faint sources, what is just background. And so just as there's been a paradigm shift within astronomy, just from generally using simple mean and variance methods to using Bayesian inference and Markov chain Monte Carlo to constrain models, one can imagine doing something similar with cataloging. And so this is precisely what I mean by probabilistic cataloging. Here I'll be considering I'll be sampling the space of all catalogs consistent with an image as opposed to just taking one such realization. And by considering an ensemble of catalogs, we can really start to address this question instead of making a deterministic claim as to each one of these regions is or is not a source or the number of sources there. We can start to quantify this probabilistically and make claims such as 80% of the time we identify, say, 20 sources here. And so in my implementation of probabilistic cataloging, so I parameterize the catalog theta with just the number of sources, their x and y positions, their fluxes, and then a series of hyperparameters here that I parameterize as beta. And so this just consists of parameters related to the PSF. So here I parameterize the PSF as a double Gaussian, and then it also consists of the exponent of the luminosity function and things of this nature. And so just generally the way the chain works here is so I first make a proposal to perturb one of the parameters. So for instance, I perturb one of the positions of the sources by a small amount. Then you can then map the model or the proposed catalog to a model image via the PSF, and then evaluate the likelihood of that model image in comparison to the real image just on a pixel by pixel level. And so after this constitutes one step, and after enough steps in the chain reaches convergence. And for our purposes, what this means is just sampling the chain is equivalent to sampling the posterior. And so my code is all in C++, and in particular, I've adapted code written by Professor Brendan Brewer of the University of Auckland. So he developed a series of software package or C++ packages to implement this method known as diffusive nested sampling that he created. So diffusive nested sampling can just be thought of as an alternative to Metropolis Hastings that's just better suited for the case in which, in our case, the catalog space has lots of local maxima. And so I've taken his code and I've adapted it so that it'll work on the images in question, and so it'll reach convergence faster. And also I've been editing the prior and things of that nature just so the convergence will be more accurate. And so there are two things to note about this implementation. So first, it's transdimensional, meaning that we're fitting for the number of sources in the image as well as these other parameters. And so, like I said, this really allows us to get at the probabilistic aspect of this cataloging. And then also, this code fits over multiple bands. And the way it accomplishes this is just it fixes the x and y positions of sources across all bands, but then it allows the fluxes to vary per band. And so here what I've done is I've just made a 2-band mock image. So here there are 25 sources pulled from a power law distribution. The fluxes have been pulled from a power law distribution with an exponent of -2. And so the red pluses here just correspond to the ground truth location of the centers of the sources. And so after 40 million steps in the chain, on the bottom here, these are model images generated from one sample from the posterior. And so the gray X's here correspond to the location of the sources as introduced by the model in this specific sample. And by eye, we can see that there's a high degree of agreement on the sources within the image of these positions. And if we actually quantify this, it's of order less than a pixel on this image. So it's doing quite well. And we can also just verify this quickly by looking at the residuals, which is just calculated as the ground truth minus the model. And so we can see that it's just basically noise, except at the locations of the brightest sources where there tends to be sort of more the higher uncertainties. But this is just naturally because the brightest pixels will have the greatest uncertainty values associated with them. And then just to confirm that the fluxes seem reasonable here, I've just plotted the cumulative luminosity function for the ground truth catalog versus the one sample or multiple samples from the posterior. And just we can confirm to first order that this looks fairly reasonable. And so then the main focus of my research, of course, is applying this to a real image. So here I'm using a DECAM image of the galactic center. So DECAM, of course, is a camera with a 2.2 degree field of view. That is the central component of the dark energy survey. And so what I've done here is I've taken a 100 by 100 pixel image in 2 bands, so the I band and R band. And So if we look closely and we keep our eyes focused down here, what I'll do is I'll flip between the real image and then the model as generated from one sample in the posterior. And so this is the result we're getting. And actually, I can flip back and forth a little bit here just to see that we're identifying all the bright sources in the image. So once again here, the gray axes are the locations of the sources in the sample. And so it is worth noting that in some cases here, just very minor, there's a tiny bit of oversplitting here, which means that the brightest sources are having an additional source introduced on top of it. And the cause of this can actually be seen if we look at the residuals up here. So if we look at the brightest sources, we see that the center has sort of characteristic red with then a characteristic blue ring around it, which is suggesting that there's a slight PSF mismatch here between the PSF of the real image and then the PSF as fit for by the model. And so the oversplitting issue is adding a faint source to try to compensate for this. And so actually if we move on to the next animation here. I'll just pull up the video. So what I've done here is I've scaled the size of the X now to correspond to the flux of the underlying source. And so this sort of gives us another dimension to see in the picture. And so once again, just to confirm, at the locations of the brightest sources, we're really just having a very faint source introduced on top. And so what I've done now is I've made an animation where I've taken samples from the posterior. And if we play it, this sort of really nicely encapsulates what probabilistic cataloging is all about. So we see that at the brightest sources, they're staying fixed in position and they're staying fixed in flux, which we can see by the X's. And so what that's telling me is that to a high degree of confidence, I know that there's a source there and I know what its flux is. Whereas if we look at sort of the fainter sources, like the ones up here, we see that they're dancing around. Sometimes they're coming in and out of the image. And of course, this is exactly the difference between that and normal cataloging software. Whereas S-Extractor would make a binary decision as to yes, we see a source there, and no, we don't. This allows us to really quantify this and make a probabilistic claim as to that we see 80% of the time a source appearing in this location. And then similarly, we can quantify overlapping sources in the same manner. So if I return to the PowerPoint. So, of course, moving forward, the one issue to be addressing is this issue of the oversplitting and the PSF mismatch that seem to be related. Of course, we didn't see this in the original mock images, and this is just because with the real image, there's no guarantee of what the PSF will be. So double Gaussian may not parameterize the PSF of the real image exactly. And also, of course, in a multiple band image, there's information being communicated through color. So one could imagine including a color prior to try to increase the rate of convergence. And so the conclusions are that, to first order, this is a viable method for cataloging, and in particular, it's able to capture two things that normal cataloging software is not necessarily capable of doing. So it's able to quantify the presence of these faint sources, as I had shown in the animation, and similarly, it can do the same thing with overlapping sources. So here's just a sample from the R band where, we can tell by eye exactly what these sources should be, but when parameterizing this with a fit, it's not necessarily so obvious how that would be done. So, probabilistic cataloging allows us to get at these issues. And so I'd just like to thank Professor Finkbeiner and Stefan Portillo for all of their mentorship and guidance, and I'd also like to thank the Astronomy 98 class. All right, so any questions?
And it's particularly important to repeat the questions.
Sure.
I think Doug is sitting in Austria watching.
Yes. Yeah. Yes.
Well, your mention of the galactic center made me wonder whether you could do this on the actual time series data of the stars orbiting the black hole in the center. And you basically could extend your model to include orbital parameters like proper motion and various proper accelerations and see if you could pull out stars that are fainter than the sort of naive detection limit in those images.
Sure. Yeah. So the suggestion was applying this to including some sort of orbital parameter to include this, around black holes or something of that nature. Yeah, that's definitely a possibility. Yeah. So ideally, if this were
That's a really hold on there. Has anybody tried that before? Because they'd be below, you wouldn't see them in any one image.
right. So I don't believe anyone has tried this before. And of course, this is particularly a case where probabilistic cataloging can be leveraged because it really allows the fainter sources to really be pushed down.
Yeah, I think that's really where this wins. That you're able to fish around at 2 to 3 sigma. I mean, the 5 sigma sources everybody finds. It's not so interesting. That's
Right.
That's not where you're making your big impact here. It's 2 to 3 sigma, where sometimes you find it, sometimes you don't. And it's a question of how much.
No, but the total sensinoids of the orbit.
Yeah, exactly. Like you can actually there, you might find it. You can pull out. They got lots of images.
Oh yeah, it's a great suggestion.
It has been done for not in the context of black hole thing, but people have tried to do shift and stack type of work on Kuiper belt objects.
Okay.
Which is vaguely related to this,
but that still requires source detection in each image.
Yes.
Right.
Okay. So there at least a way to implement it.
Kuiper belt, what they do is they basically take out the they have all their images and they shift them according to the reflex motion in the Kuiper belt, and they look for or they put on a hypothesis of a given proper motion and they look for things that stack in that space.
Great.
Okay. Other questions?
Yeah. How have you and how do you plan on dealing with the oversplitting that you were talking about?
Right. So the question was how to address the issue of oversplitting. And so, of course, I'm not really entirely sure about the cause. So one source of the issue originally was just the way just including the prior here on the number of sources. So in the original implementation, the prior on the number of sources was uniform. And so what this ended up favoring was just an enormous number of sources in the image. So like 500 sources in that region, which is clearly overestimating it. So what I ended up doing was changing the prior so that the prior is actually on DNDF, where I mean the number of sources per given flux. And so what this does is one can think about it as sort of like being a log uniform prior. That really sort of favors placing fewer and fewer sources in the image. So one could imagine maybe possibly changing the prior like that. Then another possible cause is just because, like I mentioned, in moving from the mock image to the real image, something in terms of the PSF is not necessarily correct. So just identifying that issue and resolving it would certainly help. Yes.
There's a question over there.
Okay, great. Yeah, I have two questions or comments. So one is related to PSF. Can you use the image of a star in your data as a PSF, or you have to very have the analytical approximation?
Sure. Okay. So the suggestion was possibly just using the PSF of one of the stars. And so the way it's currently implemented is the PSF is parameterized by so the widths of the two Gaussians, then sort of a weight between the two, as well as an angle of inclination and angle of ellipticity, and also potentially ellipticity. So of course, how one parameterizes this has a drastic impact. What I haven't explored with yet is hard coding in what one would expect the prior, or what one would expect the PSF to be. That would certainly help, and that's something I'd definitely worth looking into. So yeah, I definitely agree that there are multiple things to be tried in terms of addressing this PSF issue.
Yeah, so. The other question was related to your assumption about the luminosity function.
Sure.
Do you have to have this data of 2 actually, or you can change it?
Sure, yeah, so.
Because if you're thinking about the stars in the galactic center, you may not follow it.
Right. And so the question was just about the exponent of the luminosity function, if that is something that's sort of hard-coded in. And so the answer is no, that's actually fit for as well for a parameter. And so, for instance, if we go back to these luminosity function plots, so the fit actually favors, when I looked through the data, I think yesterday, it's favoring actually placing the exponent of being -2 between, with plus or minus 1, or plus or minus 0.1. And so what this is saying is that it's actually, the fit is actually quite capable of identifying this exponent without having a priori knowledge of it going in. Oh, yes?
Just a thought, since the dark energy camera does not have an atmospheric dispersion corrector, a cool thing you could do with this forward modeling trick is actually do differential chromatic refraction by simultaneously feeding for the SED depositions and the colors, and actually back out the sort of in-band spectral slope to have those positions shift around. It could be really cool.
Great, yeah, certainly.
Okay. Well, we should probably cut it off, but let's thank you again first. All right. Meg's up next, so if you could hand her the microphone, please. There you go.
Thank you.
And again, if you want to
All right.
yeah.
Here? Okay.
Did we rename?
Yeah, it says Meg pen that out? It's
That would be
right
nice.
there. Yeah. Okay. You should probably, if you scroll up and hit the, excellent. Great.
Okay. All right. So our next speaker is Meg Mehta, who's going to talk about a faster way to compute the two-point correlation function.
Okay. All right. Thank you. So I'm Meg, and I've been working with Professor Eisenstein, and actually indirectly with Zach, on a project to use fast Fourier transforms to calculate the two-point correlation function for a galaxy sample or a mock galaxy sample based off of the Sloan Digital Sky Survey. So today I'm going to talk to you briefly about the background on baryon acoustic oscillations and this characteristic distance scale that we look for in viewing galaxy clustering. Then I'm going to talk a bit about the approach to the correlation function that we used. And then I'm going to talk about the results, some of the challenges and ways to move forward with the results. And then I will have questions, which will be awesome. Okay, so some brief background on baryon acoustic oscillations and what I'm looking for when I'm looking at galaxy samples. So in the very early universe, baryonic matter and photons were coupled. And sound waves, spherical sound waves, were propagating through this early medium out from over densities in the baryon photon stuff. And so that was going on, but at about 380,000 years after the Big Bang, photons and baryons decoupled, and so these photons raced off and went into the CMB. And so you see the remnants of these spherical sound waves overlapping at all different places in the CMB anisotropies. And you also see the remnants of the baryons that were left behind at this time in galaxy clustering, where you have this characteristic distance that's overly likely to be seen between one galaxy and another galaxy in the sample that you look at. So here's a plot from something that Professor Eisenstein wrote several years ago. And it shows, it's just sort of a simulation, and you've got a central mass density, and then you have sort of a circular ring that also has a density of mass. And this shows what it might look like if you had a bunch of these spherical rings caused by matter being expelled and then dropped off at some point in recombination, overlapping. And as you can see, it's a mess. But if we look at large galaxy samples and at the statistics of these large galaxy samples, we can retrieve something that looks more like point A and see some underlying large-scale structure from a large sample. Okay, so what are we doing? We're looking for the two-point correlation function, which is essentially, if you have one galaxy in your sample, what is the likelihood that you're going to get another galaxy at a certain radial distance from the first? And we represent it as a histogram of counts of how much stuff is at how much radial distance from how much other stuff in this sample. So I've plotted here like a little chunk of the mock sample that I'm working with. Units are all in megaparsecs. And you can see each dot is going to represent a galaxy that is fake observed. And there's like kind of some structure in here. It's not completely uniform. And I put some circles on here just representing how, when you're traditionally looking at the two-point correlation function, you look at every point in the sample and you say, at some radius or in some radial bin outside of this imaginary point that you can't see, how much stuff is there. And so you'll get overlapping radii, much like you can see in here. And that's how it's typically done. All right. So what do we see? We see something that looks like this. This is my calculation of the two-point correlation function for a collection of mock catalogs. And so on this axis, you've got the radial separation of something from each element in the survey, and then you've got some counts up there. And as you go out, there's less stuff. And you can see right in here, there's this little bump. And this little bump represents the BAO peak, which is that characteristic distance that there's a little bit more of galaxies from other galaxies at it. Okay. So oftentimes, when people try to look at the two-point correlation function, they say, okay, we can observe the clustering along the line of sight in our survey, and clustering is going to be isotropic. In all of the directions, it's just going to be like that. But we want to be sensitive to anisotropy in clustering, because what happens is like the peculiar velocities of the galaxy sample that you're looking at can mess with the redshifts you observe. So I've plotted some stuff from a 2012 paper, and on the left is a two-dimensional plot of the two-point correlation function. The x-axis is like looking parallel to the line of sight, and the y-axis is looking along the line of sight in your sample. And you can see there's like a central, like hotter zone in the color plot where there's going to be more stuff closer to other stuff. And then you have that secondary ring, which is the BAO peak, which is this characteristic distance that we see between galaxies that comes out of the early universe. And this is a plot of the correlation function for the same thing in redshift space. And we can see that there's been some squishing going on here that's not isotropic in X and Y. and that's due to peculiar velocities, among other things. So our approach is going to attempt to understand and keep track of anisotropies in clustering, not just isotropic clustering. Okay, so I'm going to give you a run-through of what it takes to estimate the two-point correlation function for a galaxy sample. This is based off of a paper by Zach Slepian and Professor Eisenstein that they put on the archive in 2015. So the commonly used way to estimate what this two-point correlation function is this top thing called the Landius-Sally estimator. And essentially, you pair count between these data minus randoms thing, where you subtract the randoms, you create a random catalog that mirrors like a uniform distribution that you would expect in your sample, and then you subtract that off from what you actually get in your sample. And you count pairs between that, and you count pairs between your randoms and your randoms. And so you're looking for sort of an overdensity of pairing in distance. And so this paper represents that in terms of separation. And here you get correlations, where you're taking a convolution, essentially, of this is the data minus randoms and the data minus randoms, and you're dividing that by a convolution of the randoms and the randoms. Or we're talking about density fields, essentially. So this is, because it's convolutions, we can do this with Fourier transforms because a convolution is just a product in Fourier space, and that is what makes this computationally useful. And the Slepian and Eisenstein paper found a way to preserve understanding of anisotropy by essentially weighting the convolution and then the thing that you're going to sort by radial bins by spherical harmonics. Because when you're taking the Fourier transform, you're taking it as like a grid. You grid the data, and so it's just like a thing. It's a flat thing. Whereas traditionally, when you're pair counting, you count separation relative to the line of sight, which goes all over your survey. So you're losing that line of sight variation if you were to grid the data and take Fourier transforms, and you can get it back by using spherical harmonics in your calculation. Okay. So this is a plot of all of the coordinates for one of the mock catalogs that I used. There's about 900,000 sample elements in here. Units are in megaparsecs. It's an oddly shaped sample mirroring SDSS. And essentially there's a lot. That's the point. There's a lot of stuff in here. So traditionally, with the pair counting method, where we take every sample element and you count the distance to every other sample element, computation time is going to scale as the number of things you have squared. If you have a lot of things, that's a lot of time. And if you're doing one of the new surveys, which could have up to 1 billion galaxies, like LSST, that's an enormous amount of time and might in fact be prohibitive, especially for 3-point correlation functions, which are also a thing you can do. So the Fourier transform method, where you take a product in Fourier space to perform the convolution instead of doing this pair counting, that scales as approximately the number of grid elements you put on side of your data. So like here, we could chunk up this data in a grid spatially, and the number of grid elements per side, square that, or just have that, and that's how much time it would take, which is a lot less. So my implementation of the code takes about 4 minutes on a laptop, whereas we calculated that it would take about an hour on that same laptop if I were to do it the pair canning method, which is a big improvement. There are some losses. You have to account for the fact that when you grid your data, you assign all of the points in the grid box to the center of the thing, so you're losing a bit of where stuff is. But if you like that time improvement and it's useful to you, then it's useful to you. It's particularly good for really large surveys where you just want to get the computation done. And it's also good for running the correlation function on a lot of mock catalogs if you need to construct a covariance matrix to understand what the error might be like in your actual calculation of the 2-point correlation function for a sample. Okay, so I used 8 mock catalogs based off of data release 12 of the Sloan Digital Sky Survey. And I got correlation function results that looked fairly similar to those obtained via the pair counting method for the same sample. There's still some noisiness, and we're testing a lot of the drawbacks that might come with taking Fourier transforms, with gridding the data like that, and then asking for annular bins of separation and other stuff like that. But it looks pretty okay. So I will show you what we got. All right. So up on the top left, you've got here a plot of the correlation function. It's just like r squared, so the radius squared times the correlation function value, drawn from a mock catalog via the pair counting method. And here you have what the Fourier transform method that I was implementing calculates, and it looks very similar. And as you can see, you can pull out this VAO peak that shows you this extra characteristic distance that you get between galaxies in your sample. And this down here is from a paper in 2012 that was an actual calculation of this function on the real sample. This is just for the mock catalog that's supposed to represent the sample. And you can see that they look fairly similar. And this is the plot of the quadrupole. So in order to discuss anisotropy and clustering, what we do is we take multipoles around the line of sight clustering we calculate via Fourier transforms. That's how you sidestep losing the line of sight going everywhere if you were to do pair counting. And so this is from the paper. This is from my calculation. And it looks, again, pretty okay. All right, so what do? We implemented this approach based on paper to calculate the two-point correlation function rather quickly for mock catalogs. There are still some issues in terms of we're not getting quite what we want in the correlation function values, and we're trying to test how much of that is attributable to fundamental issues in gridding, fundamental issues in what we're asking when we ask for chunks of separation in radial bins. And overall, though, it's very fast. It's a factor 5 to 10 faster in terms of how long it takes for you to run it on a laptop, which you can do conveniently. And it will be very useful for large surveys when you just actually want to find something. Okay, so I'd like to thank my professor. I'd like to thank my other professor. I'd like to thank all of you. Questions?
So on the slide with the comparison of the two-point functions, they look very similar except for that first bin.
I'm ignoring the first bins. So in the really low separation bins, part of the whole gridding thing, when you ask for like all of your stuff in a certain grid box to go in the center of the grid box, is that you don't have that many locations for your galaxies. And so when you're taking very, very small radial bins that may only hold a few grid boxes at all, then things could get kind of hinky and you could not really get something faithful to what is in that region. So we've not been paying huge attention to the lower separation bins, especially because the target is the BAO peak. And if we're going to work towards gridding more finely, and that might help a bit.
So what gridding are you using now, and does the point where these two guys start to agree with each other actually sort of have a diagnostic of where grid effects?
Okay, so we're gridding, the grid box now is about 7 megaparsecs across. I am actually, this week, going to go home and test how different binning versus gridding comparisons affects things. That's next on the agenda, but that is definitely very high on the agenda. Yeah.
Do you have any idea about the minimum resolution you need on the grid to be able to resolve the BA?
Actually, we were just talking today that there may not be a hard and fast rule. Also, because of what you ask when you grid the data may smooth out the BAO peak from what it actually is. So it's like, there's this whole trade-off thing of like, how you bin the data like squishes it a bit, but then like how you ask to bin the data radially also does other things. It's essentially better safe than sorry. I would like to keep my separation binning way bigger than the gridding, but right now that's not quite happening.
So regarding the binning, you know, the redshift space distortions move things along the line of sight, but not perpendicular to it. So wouldn't one be concerned that taking sort of square bins that have two sides that are the same length actually isn't doing the same resolution into the data because you have more squishing along the line of sight, so you're effectively, by using the same bin length along a perpendicular line of sight, you're actually doing lower resolution along the line of sight.
Okay, I'm trying to visualize that. I mean, the answer is maybe. Like, yeah.
It sounds like you're making a recommendation. Or how to.
I don't know how to fix that one.
Yeah.
So I'm curious to know, for the advanced the upcoming surveys, the future surveys that you talked about, do you know, they must have a data analysis plan. They wouldn't get us.
I'm sure.
Is some kind of binned approach the data analysis plan, or do they think they actually can do the analysis with simple pair counting?
I haven't looked. I will look. I think overall it's useful just in itself, but I will definitely go and look.
Okay. Any final questions? Great. Okay. Let's thank Meg.
scoot that up your sweater a little bit there. Yeah. And then there's two actual points.
Oh, okay.
Okay, so our next speaker is Anne-Marie. She's going to talk about the bow shock in the cluster associated with the radio galaxy 3C438. Okay.
Thank you. Hi, everyone. I have been working with Ákos Bogdan, analyzing a disturbance in the galaxy cluster associated with radio galaxy 3C438. And here I present the observance of bow shock. So, galaxy clusters are the largest bound structures known, and it is believed that the most massive clusters are formed via the mergers of smaller subclusters. And in the event of mergers, there are often interesting features to be seen within the clusters, such as shock fronts, cold fronts, sloshing as shown in the example of the Perseus cluster, and bow shock as shown in the instance of the Bullet cluster. And these events are important as they, observances of these events are important as they offer an opportunity to study gas dynamics and shock physics, fields which are not yet fully understood. The cluster that I'm looking at is the cluster associated with radio galaxy 3C438. It is located at a redshift of 0.29, and it is a very hot cluster. It has an average temperature of approximately 11 keV. And as you can see in the image of the cluster here, there are some interesting features to be noted, discontinuities in the surface brightness. And the first discontinuity, you can see here, has an irregular shape, and you can see that it decreases fairly drastically. And then we have a second discontinuity, as if you zoom out a little more, right along here. And these are located at 90 arcseconds away from the center of the cluster core, which corresponds to a distance of approximately 400 kiloparseconds. And the second discontinuity is located at 150 arcseconds from the cluster core, which is approximately 650 kiloparseconds. So the data that I'm working with was taken by the Chandra telescope. The Chandra telescope, in this case, is the ideal telescope to use, as it has very good angular resolution. Approximately half an arcsecond is resolved in a single pixel. And so this is necessary to make out all of the features of our cluster. And with the three observations, I had a total exposure time of 153 kiloseconds. To work with this data, I had to reprocess it, remove point sources, and find and exclude the contaminated intervals of the exposure time due to flares. And I also had to create exposure maps in order to account for vignetting effects. So the first thing I did was to look into these discontinuities and confirm their presence and their magnitudes. So here I created surface brightness profiles, and they were created for the regions shown in the image here. The first region to the right, which corresponds to the west, had a surface brightness profile as shown in this plot here to the right. And it's a fairly continuous decrease in the surface brightness, so there aren't any notable features of interest. However, for this second region to the lower left, which corresponds to the east, we had two significant surface brightness jumps. And you can see them here. The first one, as expected, is located around 90 arcseconds, and the second was located around 150 arcseconds away from the cluster center. And this first jump has a decrease in surface brightness by a factor of almost 10, and the second one has a jump by a factor of nearly 4. So these are fairly significant jumps. To further understand what's going on, I wanted to look into the characteristics of the gas within the cluster. And so I proceeded to find the density profiles of the gas. I did this using a software called Profit, and using Profit, a deprojected surface brightness profile was created, and then using a broken beta model and a power law, there was a fit was also found for the density. And so ProFit found that we had a density drop at the innermost discontinuity of a factor of 2.3. And in the outer discontinuity, we had a density drop by a factor of 4, which is very large. The next thing we wanted to understand is the temperature of the gas within our cluster. And so I did this by using the software XSpec, and XSpec used an APEC model to fit the spectral distribution, the spectral energy distribution of the photons from our cluster. And using the regions shown here, I found the temperatures for each bin, and the temperature profile is shown here. And as noted, we have a temperature increase by a factor of 1.9 at 90 arc seconds, and then a temperature drop by a factor of 1.7 at 150 arc seconds. So now that we have our temperature profile and our densities, we can compute the pressures. And this is just done using the standard ideal gas law. And so I found that, interestingly, the pressure along this first discontinuity was fairly continuous. We only saw a pressure drop by a factor of 1.2. On the second discontinuity, however, we had a pressure drop by a factor of 7.1, which is a very large pressure jump. And there are 3 important features to be noted from this. First, based on our densities, our temperatures, and the pressures, going from a low temperature to a high temperature and having a fairly continuous pressure, we can conclude that there is a cold front located here. And then going from high temperature to low temperature with a big drop in pressure, we're able to conclude that we have a shock front here. And finally, based on the somewhat cone-like feature of this discontinuity, as you can see here, and the magnitude of this drop, we considered that this might be an example of bow shock. So looking into bow shock, we had to compute the velocity of our cluster, the gas within the cluster. So bow shock is when your bulk velocity exceeds the speed of sound. And so using the Rankine-Hugoniot shock equations, I was able to find that the bulk velocity of our cluster it has a Mach number of 2.1. And so this corresponds to a velocity of 2,400 kilometers per second within the plasma of our cluster. So we do indeed have bow shock here. And furthermore, based on the cold front and shock features that we'd seen, which are characteristic of major mergers, we have concluded that this cluster is likely undergoing a major merger, which is 2 clusters of equivalent magnitude merging. This is a significant finding, namely because there have been very few examples of bow shock that have been observed within clusters. So this offers a great opportunity to further study the gas dynamics within this cluster. So in summary, we have found that the cause of the disturbances within our cluster are first a major merger, and we tentatively believe that this might be a major merger between 2 non-cool core clusters based on some of the characteristics and features we see in this cluster. Furthermore, we were able to find the bulk velocity to be 2,400, which is a supersonic velocity, and so we conclude that there is bow shock in our cluster. And finally, I would like to thank my advisor, Akos Bogdan, William Foreman, Professor Charbonneau, and the Astronomy 98 class for their immeasurable support and assistance throughout the semester. Questions?
I understood you properly. You're deriving the 2,400 kilometers a second based on the temperature and pressure jumps across these fronts.
Yes.
Does that also make a prediction for the angle of the bow shock, the angle of the cone of expansion?
So that has not been addressed.
Please repeat the question.
Oh yes, I'm sorry. So the question was the wedges or the regions that were used to develop the profiles were not centered exactly at the core, and he was asking if the angles of the wedges themselves were addressed.
Well, I thought
No, you're asking the shape of the actual structure.
If you shot something through at higher speed, that the bow shock was more had a sharper angle than if you shoot it through very slowly. But the speed at which you shoot them would, that the projectile goes through indicates the angle of the cone of the bow shock.
The speed at which you project.
Just forget about clusters. If you just have an ambient medium and you shoot some projectile through, I thought that the bow shock basically spread out at the angle, the opening angle of the cone of the bow shock behind the projectile depended upon the speed of the projectile.
Yes.
So I'm just wondering whether whether Mach 2 is consistent with the angle of the bow shock that you see morphologically in the picture.
That is a good question, and I have not had the opportunity to look into that yet. Our finding for the Mach number has some error, so there is room for it might be a little less than this. However, we're fairly confident that that this is bow shock. As to the magnitude of it, that's somewhat tentative.
Would you mind just putting the picture up?
Mm-hmm.
Can you just outline with the label formula
Yep.
the shape that you see?
So it extends from here and then comes out that way. Yeah. Mm-hmm.
So here, you're assuming that, what is the L and the M range of the subscripts in the pressure equation?
Oh, I'm sorry. That's just for the label for the region that I'm using. So, like I would call this region 1, 2, 3, and so it would be the comparison, the ratio between regions bordering each other.
Yeah, I guess I'm wondering, if you go back to that, does this assume anything about the regions all being in some sort of equilibrium with each other, or within each region that it's in pressure equilibrium so that the ideal gas law is transient? I think those are probably the second thing. I said is what it assumes, but is that right?
Yes, it does make some assumptions, and the assumptions are most likely accurate enough that these values can be, or that our conclusions on the pressure jumps are accurate enough, I suppose.
Yeah, I guess I just wondered, because if it's really a major merger, that's a really violent event.
Mm-hmm.
Like the swirling picture you showed at the
Right.
beginning, and it seems like at least at some point after it, things wouldn't be in equilibrium yet. But maybe if you take small enough regions, then this argument still works, or maybe it's long enough after the thing that it's fine.
Yeah, yeah. Sorry, the using smaller regions, it is, I believe, safe to make that assumption.
And I'm sorry, can you? I don't know if you ever showed an image of the galaxy. So there's an optical.
Yeah. So
galaxy,
actually,
and where does it? How big is it compared to all this?
So the it's an AGN. It's located right here, and so it's not energetic enough to have created the disturbances that we see.
Right. Yeah. And has this data been published before, or is this?
So there was an initial observation in 2002, which noticed these discontinuities. However, there wasn't much follow-up as for a concrete conclusion. And so there was a follow-up observation in 2011, and this project here is addressing the proposal for that.
I see.
Yeah.
Great. Okay. Okay. Any final questions? All right. Let's thank you again. Time for our last speaker. You could hand over the microphone, please.
FC, yeah.
Okay, so our final presenter today is Francesca Childs. We'll be talking about designing a lab for the old astronomy project.
All right. Hello, everybody. Good afternoon. My name is Francesca, and this semester I was working with Professor Goodman on designing a lab for the old astronomy project, which is focusing on how to put images from astronomy articles back on the sky in Worldwide Telescope. So you may have heard of the ADS All Skies Survey, which is this website where you can go on and actually, let's see if this is working. Yeah, so you can change how you view the sky, and then you can also, in a second, you can show the sources, and then when you go in and zoom in and click on one of these red dots, it'll actually bring up all the articles ever published about this object, and then you can view them online. And so the old astronomy aspect of this project is doing the same thing for images. So perhaps you are exploring the web and you see a really beautiful image that you want to see on the, like where it belongs on the sky. So you can upload it into Flickr, and this astrometry.net robot will try to solve the image and place it on the sky in Worldwide Telescope. And you can change how you view it, and that is actually where it belongs. And so there are a lot of images in astronomy articles. There's like over 3.2 million. And not all of them can be solved by the astrometry.net robot. And so we need humans to go through and actually add data and coordinates to the images so they can be solved and placed on the sky in Worldwide Telescope. And so this is taking the form of a citizen science project. There are two major platforms for citizen science projects. One is Zooniverse, and they currently have 6 ongoing astronomy research projects. And the other one is CosmoQuest, which has 4 ongoing research projects. And both of them ask interested scientists to log into their website and kind of look at images and find patterns or identify certain coordinates in order to add them to a larger database. And so Old Astronomy is going to be added to the Zooniverse website, and we're going to ask lots of people to go on and add information to these coordinates. And some of the people we want to do that are high school students. And so my focus was really how to get high school students most involved in the project and what would they find most interesting. So the design of my project was to go into a high school, which I thought would look something like this, looked a little bit more like this. So I went to 2 different high schools. I went to the Cambridge Rindge and Latin School, which is a public school down the street from Sanders Theater, and then I also went to Milton School, which is a private school just outside the city. And I talked to 37 students. And I described the process of the lab to them, which I'll show you in a bit, and then I asked them to fill out a survey. So it was I kind of had to classify it as a focus group because I only talked to 37 students, and so the N was very small. And then I would have a conversation with these students and kind of get their recommendations on what would make the lab most exciting to them. And so before I went and talked to any students, we had an idea of what we thought the lab should look like. We thought it would be groups of students working together to analyze 10 to 12 images and go through this whole process. And then they would choose, that's kind of the second step, and then they would choose the most interesting object out of those 10 images they solved or they added data to in order to do a final paper on. So they would kind of have to work like that. And so then there were 2 additional features that I described to the students. One would be that they could interact with other students who are completing the lab across the country and kind of troubleshoot problems. Maybe if they found one really interesting image they wanted to share with everyone else, kind of a social media-esque platform for the students in the lab. And then the second kind of optional feature would be that the best final papers would be published on the web in the ADS, kind of on the abstract page of an article. And then I described to the students how the lab would proceed. So the first thing they would do is they would get an image like this, and they would have the first question: is this image one or many? Clearly, this image here has many sub-images, but not all of them would, and so they would select many, which would take them on to the next step. If it was just one image, they'd just skip this step and go on. But here they would have to draw rectangles around the different images, and then these would be put back in the system to be solved again. And so they would get an image, that was one, and they would have to identify what type of image this is. This step's really important because a lot of images in articles are not even of the sky. They're of a scientist in a lab or maybe a graph. And so we don't want to spend time, we can't place those on the sky. So it's important to just identify that this is a photograph of the sky and it's a contour map. The next step is to identify the coordinates, and this is probably the most important step because this is how you can actually place it on the sky in a worldwide telescope. And so students would have to know enough about astronomy to identify like the RA and the DEC, or the axes, and then also what these different numbers along the bottom mean. And so they would identify what the axes are, draw lines, and mark what value those lines have. And then they could adjust the contrast and the brightness in order to best bring out the stars in their image. They would save it, and then there's an optional feature where they can talk to a professional scientist and ask questions. And so if a motivated student was interested, they could go online and ask a scientist a question like, is this a supernova or remnant or a giant molecular cloud? And it would be answered within 2 or 3 days by a professional scientist who volunteered their time. And then they would have successfully solved an image, which we will see in a second, appear on Worldwide Telescope. So here's the same image we've been working with. You can actually see there it is overlaid with an image from the All Sky Survey, which is pretty cool. And ideally, this would work with all images of the sky that have ever been published. So after showing the students this demonstration, I asked them to fill out a survey. The survey asked a variety of questions, like trying to figure out what they would be most interested in. Like, I want to work with scientists on a global collaboration. I want to work with real data. I like to explore historic images of the sky. I feel important helping scientists. I want to interact with other students. I want my final project to be published on the web. I enjoy looking at pretty scientific images. I mean, that one I feel like everybody does. And then maybe they're interested in the history of astronomy. Maybe they like doing online labs. Group work was a question, whether or not students would be react positively to that. And then if we wanted to know if the students were actually just interested in astronomy. And so here are the results that I found. You'll see a dotted line on the box. That's the mean. The median is in a solid line. Milton is the orange, and that's the private school I visited, and then CRLS is the public school, the Cambridge Rindge and Latin School, in the green, or in the blue, and then both responses are on the green. And so you can see that I've ordered it from most positive responses downward, so everybody likes the pretty scientific images. Most people were interested in astronomy and liked working with real data. The 1 corresponds to strongly disagree, and the 5 to strongly agree, so the 3 is kind of neutral, so all responses were above a 3 mostly, so overall students were very positive to it. The least positive responses were to group work, interaction with other students, history of astronomy, and online labs. So we kind of had to rethink our idea of the lab in response to group work. The next thing I asked students to do was answer a free response question, and these are a selection of the responses that I got from them. Some were like, looks cool, I like this. I don't see any benefit for students. Be more elaborate, explain it more. Some liked learning about the different websites. And so it was just kind of like a collage of all these different responses that then I went through and categorized them into these 4 general categories. And those were the percent of respondents. So 60% of people who responded to the open question thought it was cool. Some were confused or it was unclear. Some just didn't see the point. Maybe it was grunt work. Some wanted other final projects instead of a final paper. So that made me think of another idea. We had to do something different than just write a final paper. And so the idea of the final paper was that once they choose their most interesting image that they were going to do a final project on, they would read the article that it originated from and learn about it. So based on the responses, I came up with 2 recommendations. Option 1 would be group work. And these 2 recommendations, it's up for the teacher of the class to kind of decide which way they want to go. So with the group work, it would be kind of like we originally envisioned. Students would be in a group of 3 or 4. They would analyze 10 to 12 images together, choose their favorite, read the article that it came from, do some further research, and then do a final project on it. The final project would either be a final paper, create a website about it, do a worldwide telescope tour, or even a 3D model. And these ideas kind of came out of conversations with different teachers and what they thought would be useful. Option 2 is kind of a peer review process where students would still have a group of 3 or 4 peers in their class, but they would individually analyze the images and individually do their own final project, and then have a peer review meeting where the group would get together and kind of review each other's, kind of like what we've been doing in this class and what is done in the actual scientific community. One aspect that students responded very positively to was the interaction with professional scientists, so I thought that was definitely important to keep that aspect of the lab. Finally, I'd like to acknowledge Professor Goodman, Pat and Aaron, Sue and Mary, who came to visit also, and Professor Sadler, and the rest of the Astronomy 98 team. That is a good question. Yeah. So that is definitely going to have to be worked out by the Zooniverse team, and their work out of Chicago, and so that'll be something that they figure out how to change between coordinates on different photos. My focus was really just on getting high school students involved, so I didn't have to think about the technical aspect. Okay, so the question was about a 3D model final project and maybe doing it 3D printed. And that would be really interesting, and I think students would respond positively to that if they have the means to like 3D print something. And so this would be like a generic lab for high school students across the country to do. But some schools, that could definitely be an option.
So, one of the tricks, the art of citizen science, is that you have to engage this broad community in being excited. So some of them are interested in cracking codes because of maybe their political beliefs or something. You know, some of them are interested in looking at planets because maybe that speaks to some part of their personal interest. One comment I saw, I was reading all the comments, was, you know, it feels like we're doing busy work that scientists themselves can't be bothered to do. Mm-hmm. So how would you cast what you're doing here? Is there a hook? You know, so it's like flipping, you know, virtually flipping through journals and cutting out images is not, what's the hook to compel them? What can we tell them? What are they able to do scientifically that isn't possible otherwise, or have you thought about that much yet?
So I think the question was how to get, what's the hook for the project and how to get students really interested in it.
Like you get to talk to scientists and all that, that's fine, but is there a hook in the act itself?
Is there a hook in the act itself of going through the process of adding data to the images? I think, as you saw from the survey, a lot of people responded positively to just like looking at pretty scientific images. And so just like exploring historical images of the sky and seeing what's out there could be a hook. Also, the final project is really cool when you can zoom around in Worldwide Telescope and see all the images that have been taken of various objects.
Yeah.
Yeah, and so their version of the baking for this is actually that step that printed out the when the image was on the sky in Worldwide Telescope, and then what she didn't show is you can then kind of change the wavelength and look at all kinds of other things about the source. So apparently they probably testing and this kind of
So that
sense of
exploration.
accomplishment of seeing your image in the context of modern imagery is what gets people. Hopefully.
And then kind of just a methods question was, you know, there must be some traditional techniques to analyze survey data like this. You must have had some students who just were submitting random responses, and there's ways to test for that. Some of your points here don't have any dispersion. I don't know if that means you've got 39 responses of all the identical number, and if that would be impossible or very worrying. So can you just tell us a little bit about how you analyze the data?
Yeah, so all questions were required to be answered. And in some cases, it was just everyone marked 5 on that. There was only one instance of a student marking 5, just like straight down the list, like he spent no time on it, and just like that was all just one answer. But overall, every response seemed to be really real and thought out. Possibly.
It's very encouraging that everyone says they're interested in astronomy, but I can tell you from people who have sat next to me on airplanes, this is not true.
Why don't you say how you actually administered the survey?
Yeah, so the survey took 3 forms. At Milton, it was just students had their own personal laptops, so they pulled them out and did the survey. At CRLS, I talked to 2 separate classes, and in the first class, it was kind of students on their cell phones filling it out, and then in the second class, the teacher didn't want students on their cell phones, so he printed it out, and so students actually had to write it down.
Again, very briefly, you know, as a pitch to astronomers, I could see some utility in being able to have an image that was published. Is it possible, could you think about people in certain journals when images are published, would make it the author's responsibility to make sure that it gets incorporated into the growing database, so that you don't always have to have, at some point, everything's done in the past, and then we're taking care of the future.
Why don't you do the recommendations of the AAS publications passports and then come to the AAS meeting in January and say that exactly that?
All right.
Okay. Well, let's first thank you again. And so that is it. So I want to say thanks to all the students. I thought the presentations were all very good, very well done, very clear. And our time together is almost at an end. We have a field trip tomorrow, so I'll see you all at 4:30. And then the final versions of your papers are due on the following Monday. Okay, so then let us thank all the students again for their talks today. And please enjoy the last bit of cider and some cookies.
Question about the hard copy.
Yeah.
How do we turn it into? So there's a Canvas submission, right? That's digital, but you want a hard copy as well.
I do, because I need that for the archive.
Okay.
So print out a nice copy. Just print it out on a CF machine. And you can print out a color version, and then just put it next to my office. There's a little table out front of my office.
Any day, Monday, or can we do Tuesday? Because as long as we have a digital submission, that meets the deadline and stuff.
Yeah, I mean, I'd like it Monday, and you might view that as an encouragement just to be done, and then you can go on to the next thing. But yes, if you do the digital, I know that you're busy at this time, so if the digital thing has to be Monday. If I get it Tuesday morning at 10 a.m. or something, that's fine. The reason is I do need a signed copy as well, and you might as well use that opportunity to plunk down the actual signed affirmation. So.
Great. Actually, I had a very quick question. Sorry, I was flipping through my PowerPoint like originally when you had talked about it. So where exactly are we supposed to meet tomorrow at 4:30?
Oh, at the Museum of Science.
Right. So is there a specific place when you go in?
Before the ticket booth, there's like a lane to go to
Yeah.
the theaters.
Gotcha.
Right, if you walk in and then you walk towards the IMAX and the planetarium, in front of the planetarium are just some great little kind of walk-up displays that you can play with. We'll be all milling around in there.
Perfect.
But try to arrive right on time because we'll have more time with the staff who at some point need to get home to their other activities. So.
All right, great. Thank you very much.
Okay.
Yeah, I just wanted to apologize for coming in late. Like I know like punctuality is like very important. Like I
You
just
were
like
not late
totally
at all.
missed something.
It was totally fine. You got here by plenty. I just want to make sure you had time to. What was great is we didn't have any technical glitches.
Right. Yeah.
And those can really sometimes derail students because they get nervous and also it delays everything. So as long as it was all fine.
Okay.
No,
All right.
no worries at all.
Sounds good.
Yeah.
I will see you tomorrow.
Good. Yeah, it should be fun. I mean, this is a fun.
Oh yeah.
Fun activity.
Do you know about when you'll be done tomorrow? Like how long?
I think I can't imagine it going more than 90 minutes. So we'd certainly be done by 6.
Okay, yeah. I'm going to take out a halfway, I think, tonight at 7, so I'll have a 24-hour pass.
Oh, I see. Yeah. Yeah.
Buy a ticket to the museum?
No. No.
We just like say
No.
we're here for class.
No. You don't. You won't go into the paid area.
Oh,
you walk
okay.
in, and you're just going to turn left because some people just go to the planetarium without actually buying a museum.
Okay.
Yeah, so don't buy a ticket. Maybe I'll send a little announcement to make it
Okay.
clear. Yeah.
I was glad about that. Although it would have been nice to get a ticket out of it.
Well, you could right. You could elect to go. Maybe with honestly a Harvard ID, you might actually get.
You don't.
something.
Only MIT. MIT
No,
gets free
museum
Museum of
of stuff.
Science. We do not.
Well, we get other things though. We do get a lot of other museums.
Yeah, but we get the MFA.
Yeah. Okay.
And the Isabel Stewart Gardner.
Well, anyway, don't buy a ticket.
Don't buy a ticket.
We're good.
Okay, good.
Yeah.